For centuries, we thought the night sky was calm, eternal stillness. But lurking in the darkness is Barnard's star, a cosmic wanderer racing through space. This unassuming red dwarf, just 6 light-years away, is no ordinary neighbor. It's moving fast, faster than any other star near us, charging forward at a staggering 31,000 miles per hour. Discovered in 1916 by astronomer E. Barnard, its speed shook the scientific world. In just 10,000 years, a blink in cosmic time, it will come dangerously close, brushing the edges of our solar system, stirring up the distant Oort cloud, and possibly sending comets raining inward. A quiet threat, hidden in plain sight. One day, this tiny star might reshape our corner of the galaxy. The question is, will we be ready? Barnard's star is a remarkable celestial object that has captured the attention of astronomers for over a century. Located just 6 light-years away from Earth, it is one of our closest stellar neighbors, surpassed in proximity only by the Alpha Centauri system. This red dwarf star is notably smaller and cooler than our Sun, with a mass about 1/6 that of our home star and a surface temperature of around 3,000 degrees Celsius. What makes Barnard's star truly fascinating is its rapid movement across our night sky. It exhibits the fastest proper motion of any known star, appearing to zip across the celestial sphere at a rate that would see it traverse the width of the full moon in a mere 180 years. This swift motion was first noticed by American astronomer Edward Emerson Barnard in 1916, hence its name. Despite its proximity and fame among astronomers, Barnard's star is too faint to be seen with the naked eye. Its dim nature is due to its classification as a red dwarf, the most common type of star in our galaxy. These stars are known for their longevity, and Barnard's star is no exception, with an estimated age of around 10 billion years, making it considerably older than our Sun. For decades, Barnard's star was thought to host planetary companions, sparking intense scientific debate and numerous observational campaigns. Recent studies have provided evidence for a super-Earth orbiting this ancient star, although confirmation of this exoplanet remains a subject of ongoing research. The star continues to be a prime target for exoplanet hunters and astrobiologists, given its proximity and the potential for habitable worlds around red dwarf stars. Barnard's star is one of our closest stellar neighbors, situated in the constellation of Ophiuchus. This red dwarf star lies just 6 light-years away from our solar system, making it the 4th nearest star to Earth after the 3 stars in the Alpha Centauri system. Despite its proximity, Barnard's star is not visible to the naked eye due to its small size and low luminosity. In galactic terms, Barnard's star is located in the Milky Way's Orion arm, the same spiral arm that houses our own solar system. It resides in what astronomers call the galactic thin disk, a region where most of the galaxy's star formation occurs. This placement puts Barnard's star relatively close to the galactic plane, the imaginary flat surface that runs through the center of our galaxy's disk. Interestingly, Barnard's star is not a stationary neighbor. It has the largest proper motion of any known star, meaning it appears to move faster across our sky than any other star. This rapid apparent movement is due to its close proximity to Earth and its high velocity relative to our solar system. Barnard's star is one of our closest stellar neighbors, residing a mere 6 light-years away from Earth. This proximity makes it the 4th closest known star system to our Sun, after the 3 stars in the Alpha Centauri system. Despite its nearness, Barnard's star is not visible to the naked eye due to its small size and low luminosity. As a red dwarf, Barnard's star is much smaller and cooler than our Sun. It has only about 16% of the Sun's mass and less than 1% of its brightness. This dim nature, combined with its close distance, has made Barnard's star a subject of great interest for astronomers studying nearby stellar objects. The star's proximity to Earth allows scientists to observe its movement across the night sky more easily than other, more distant stars. In fact, Barnard's star holds the record for the largest proper motion of any known star, appearing to move faster across the celestial sphere than any other star from our vantage point on Earth. This cosmic neighbor has been the focus of numerous studies, including searches for exoplanets. Recent observations have suggested the presence of a super-Earth orbiting Barnard's star, though this finding is still under scrutiny. The ongoing research into this nearby star system continues to provide valuable insights into the nature of red dwarfs and the potential for life-supporting planets around them. Barnard's star was first discovered in 1916 by American astronomer Edward Emerson Barnard. This red dwarf star caught the attention of astronomers due to its exceptionally high proper motion across the night sky. In fact, Barnard's star moves faster than any other known star relative to our solar system, covering a distance equal to the Moon's diameter every 180 years. Despite being one of our closest stellar neighbors at just under 6 light-years away, Barnard's star is not visible to the naked eye due to its small size and low luminosity. It is classified as a red dwarf, much smaller and cooler than our Sun, with only about 15% of the Sun's mass and less than 1,000th of its brightness. The discovery of Barnard's star marked a significant moment in astronomical history, as it helped astronomers better understand the diversity of stars in our galactic neighborhood. Its rapid motion across the sky has made it a valuable target for studying stellar properties and searching for potential exoplanets. Edward Emerson Barnard, an American astronomer, discovered the star that now bears his name in 1916. Barnard's star quickly gained fame in the astronomical community due to its unique characteristics. It boasts the fastest proper motion of any known star, meaning it appears to move across the night sky more rapidly than any other stellar object visible from Earth. This red dwarf star is located in the constellation Ophiuchus and is one of our closest stellar neighbors, sitting just under 6 light-years away from our solar system. Its proximity and high proper motion made it an object of great interest for astronomers studying nearby stars and their movements through space. Barnard's discovery was particularly impressive given the technological limitations of early 20th century astronomy. He used a telescope at Yerkes Observatory to detect the star's rapid motion, showcasing his exceptional observational skills. This find significantly contributed to our understanding of the local stellar neighborhood and helped refine techniques for measuring stellar distances and movements. The star has since been the subject of numerous studies and has played a role in the search for exoplanets, though no confirmed planets have been found orbiting it to date. Barnard's star remains a testament to the power of careful observation and the ongoing importance of studying even the seemingly unremarkable stars in our cosmic backyard. Barnard's star holds a special place in astronomical research due to its unique characteristics and proximity to our solar system. Located just 6 light-years away, it ranks as the 4th closest star to Earth, making it an ideal subject for detailed observation and study. This celestial neighbor first caught the attention of astronomers because of its exceptionally rapid motion across the night sky. Barnard's star exhibits the fastest proper motion of any known star, moving at a rate that would see it traverse the width of the full moon in a mere 180 years. This swift movement allowed astronomers to detect and measure it with remarkable precision, providing valuable data for understanding stellar dynamics. Barnard's star is also noteworthy for being a red dwarf, the most common type of star in our galaxy. Its study offers insights into the life cycles and behavior of these numerous yet often overlooked stellar objects. Despite its proximity, Barnard's star is too faint to be seen with the naked eye, highlighting the vast range of stellar brightnesses in our cosmic neighborhood. The star has been the subject of intense planet hunting efforts for decades. While early claims of planetary companions were later disproven, recent observations have suggested the presence of at least one super-Earth orbiting this ancient star. This discovery not only expands our understanding of planetary formation around different star types, but also brings the search for potentially habitable worlds closer to home. Barnard's star, one of our closest stellar neighbors, is a stark contrast to our Sun in both size and mass. This diminutive star is a red dwarf, belonging to a class of stars that are the most common in our galaxy. Despite its proximity, Barnard's star is invisible to the naked eye due to its small size and low luminosity. In terms of size, Barnard's star is significantly smaller than our Sun. Its radius is estimated to be only about 15 to 20% that of our Sun. To put this into perspective, if we were to replace our Sun with Barnard's star, it would appear as a small, faint red orb in our sky, providing far less light and heat to Earth. The mass of Barnard's star is also considerably less than that of our Sun. Astronomers estimate its mass to be roughly 14 to 17% of our Sun's mass. This low mass is typical for red dwarf stars, which are much cooler and less energetic than stars like our Sun. Despite its small size and low mass, Barnard's star has captured the attention of astronomers for decades. Its proximity to Earth and its high proper motion across our sky make it an intriguing subject for study, offering insights into the nature and evolution of the most abundant type of star in our universe. Barnard's star is a red dwarf, one of the most common types of stars in our galaxy. This small, cool star is much less massive and luminous than our Sun. Red dwarfs are known for their longevity, burning their fuel slowly and steadily over incredibly long periods of time. Located just 6 light-years away from Earth, Barnard's star is our fourth nearest stellar neighbor. Despite its proximity, it cannot be seen with the naked eye due to its low luminosity. This star has fascinated astronomers for over a century because of its rapid proper motion across the night sky, moving faster than any other known star relative to Earth. Barnard's star is estimated to be around 10 billion years old, making it considerably older than our Sun. Its age and stability make it an intriguing target for exoplanet searches, as any planets orbiting it would have had ample time to develop and potentially support life. Recent observations have suggested the presence of a super-Earth orbiting Barnard's star, although this finding is still debated among astronomers. The study of this nearby red dwarf continues to provide valuable insights into stellar evolution and the potential for habitable worlds around the most common stars in our universe. Barnard's star, one of our closest stellar neighbors, is an ancient resident of our galactic neighborhood. Astronomers estimate this dim red dwarf to be approximately 10 billion years old, making it more than twice the age of our Sun. This venerable star has been steadily burning since the early days of our Milky Way galaxy, witnessing countless cosmic events throughout its long existence. The age of Barnard's star is determined through a combination of observational data and stellar evolution models. Its low mass and cool temperature are indicative of its advanced age, as smaller stars like red dwarfs burn their fuel much more slowly and efficiently than larger stars. This slow burn rate allows them to remain stable for incredibly long periods, far outlasting their more massive counterparts. Despite its age, Barnard's star continues to be a subject of fascination for astronomers. Its proximity to Earth, at just about 6 light-years away, makes it an ideal target for studying the properties and behavior of old, low-mass stars. The star's advanced age also provides valuable insights into the early history of our galaxy and the processes of stellar formation and evolution over cosmic timescales. Barnard's star has earned its reputation as a runaway star due to its exceptionally rapid motion across our night sky. This small, dim red dwarf is racing through space at a staggering speed of about 140 kilometers per second relative to our Sun. To put this into perspective, it's moving fast enough to traverse the diameter of the full moon in a human lifetime. This swift movement is not just impressive in its speed, but also in its visibility. Barnard's star exhibits the largest proper motion of any known star, meaning it appears to shift its position against the background of more distant stars faster than any other stellar object we've observed. This rapid apparent movement was first detected by astronomer E. Barnard in 1916, hence the star's name. The cause of Barnard's star's high velocity is rooted in its age and history. Astronomers believe it to be one of the oldest stars in our galaxy, possibly nearly as old as the universe itself. Over its long lifetime, gravitational interactions with other stars and massive objects have likely accelerated it to its current breakneck pace. Despite its speed, Barnard's star is actually one of our closest stellar neighbors, located just about 6 light-years away from Earth. Its combination of proximity and high velocity makes it a unique and important object of study for astronomers seeking to understand stellar motion and the history of our galactic neighborhood. The discovery of Barnard's star is a fascinating tale of astronomical perseverance and keen observation. In the early 20th century, American astronomer Edward Emerson Barnard was meticulously studying photographic plates of the night sky. His careful examination revealed something extraordinary, a faint star that appeared to be moving rapidly across the celestial sphere. Barnard's discovery in 1916 was groundbreaking because this star, later named after him, exhibited the largest proper motion of any known star. Proper motion refers to the apparent movement of a star across the sky, as seen from Earth. The rapid motion of Barnard's star indicated that it was relatively close to our solar system. This proximity made Barnard's star an object of great interest to astronomers. At just 6 light-years away, it became known as the second closest star system to Earth, after the Alpha Centauri system. The star's nearness and its high proper motion provided valuable opportunities for scientists to study stellar properties and movement. Barnard's meticulous work and his discovery highlight the importance of patient, detailed observation in astronomy. His finding not only added a new member to our list of nearby stellar neighbors, but also opened up new avenues for studying low-mass stars and the dynamics of our local stellar environment. Barnard's star was discovered in 1916 by American astronomer Edward Emerson Barnard. He detected this faint red dwarf star through careful observation and comparison of photographic plates taken over time. Barnard noticed that one particular star was moving rapidly across the sky relative to other stars in its vicinity. This movement, known as proper motion, is the apparent change in position of a star as seen from Earth. Barnard's star has the fastest proper motion of any known star, moving about 10 arcseconds per year. This is equivalent to the width of a human hair viewed from 66 feet away. The detection of Barnard's star was a significant achievement in early 20th century astronomy. It demonstrated the power of long-term, systematic observations and the importance of patience in astronomical research. The star's rapid motion across the sky also hinted at its close proximity to our solar system. Despite being one of our nearest stellar neighbors at just 6 light-years away, Barnard's star is not visible to the naked eye due to its low luminosity. Its discovery and subsequent study have provided valuable insights into the nature of red dwarf stars and the diversity of our galactic neighborhood. The initial observation of Barnard's star relied on relatively simple yet effective tools available to astronomers in the early 20th century. Edward Emerson Barnard, the American astronomer who discovered the star in 1916, primarily used a large refracting telescope at Yerkes Observatory in Wisconsin. This telescope, with its 40-inch diameter lens, was one of the most powerful instruments of its time, allowing Barnard to detect the faint red dwarf star despite its low luminosity. Barnard's observations were complemented by photographic plates which were crucial for recording and analyzing stellar positions and movements. These glass plates, coated with light-sensitive emulsions, captured images of the night sky over long exposure times. By comparing plates taken at different times, Barnard was able to detect the star's rapid proper motion across the celestial sphere. Precise timekeeping devices were also essential for these observations. Accurate clocks allowed astronomers to track the exact moments of stellar positions, which was crucial for measuring the star's movement over time. Additionally, Barnard likely used a blink comparator, a device that rapidly alternated between two photographic plates, making it easier to spot objects that had moved between exposures. These tools, though considered rudimentary by modern standards, were state-of-the-art at the time and allowed for the groundbreaking discovery of what would become known as the fastest-moving star in our night sky as seen from Earth. Barnard's star has been a subject of fascination for astronomers since its discovery in 1916 by American astronomer Edward Emerson Barnard. Initially, this red dwarf star caught attention due to its exceptionally high proper motion across the night sky, moving at a rate of 10 arc-seconds per year. This rapid movement indicated that Barnard's star was relatively close to our solar system, making it an ideal candidate for studying nearby stellar objects. In the 1960s, controversy arose when astronomer Peter van der Kamp claimed to have detected planetary companions orbiting Barnard's star. He based this conclusion on apparent wobbles in the star's motion, which he interpreted as gravitational influences from orbiting planets. However, subsequent studies and more advanced observational techniques failed to confirm these findings, and the scientific community eventually dismissed van der Kamp's planetary claims. The advent of more sophisticated detection methods in recent decades has significantly advanced our understanding of Barnard's star. High-precision radial velocity measurements and advanced data analysis techniques have allowed astronomers to probe its environment with unprecedented accuracy. These efforts culminated in the 2018 announcement of a candidate exoplanet orbiting Barnard's star. This potential planet, designated Barnard Star B, is believed to be a super-Earth with a mass about 3 times that of our planet, orbiting its host star every 233 days. While the existence of Barnard Star B still requires further confirmation, this discovery represents a significant milestone in our evolving understanding of this nearby stellar neighbor. It demonstrates how technological advancements and persistent scientific inquiry can reveal new insights about even well-studied celestial objects, constantly reshaping our knowledge of the cosmos. Edward Emerson Barnard, a renowned American astronomer, played a crucial role in the discovery and naming of Barnard's star. In 1916, while working at Yerkes Observatory, Barnard noticed a faint star with an exceptionally high proper motion. This means the star appeared to move rapidly across the night sky compared to other stars. Barnard's keen eye and meticulous observations led him to recognize this star as the fastest-moving star known at that time. His discovery was particularly impressive given the technological limitations of early 20th century astronomy. Barnard used a technique called blink comparison, where he rapidly switched between photographic plates taken at different times to detect stellar movement. The star's rapid motion across the sky indicated its close proximity to our solar system. This proximity, combined with its high proper motion, made Barnard's star a subject of great interest in the astronomical community. As a result of his groundbreaking work, the star was named after him, cementing Edward Emerson Barnard's legacy in the annals of stellar astronomy. Barnard's discovery highlighted the importance of patient, detailed observation in astronomy and demonstrated that even in the modern era, individual astronomers could make significant contributions to our understanding of the cosmos. Barnard's star, discovered in 1916 by American astronomer Edward Emerson Barnard, revolutionized our understanding of stellar motion and nearby celestial objects. This red dwarf star, located just 6 light-years from Earth, captured the attention of astronomers due to its exceptionally high proper motion across the night sky. The discovery of Barnard's star provided astronomers with a unique opportunity to study a nearby stellar neighbor in great detail. Its proximity and rapid movement allowed scientists to measure its parallax with unprecedented accuracy, refining our methods for determining stellar distances. This breakthrough improved our understanding of the cosmic distance ladder, a crucial tool for measuring vast cosmic scales. Furthermore, Barnard's star became a prime target in the search for exoplanets. Its close proximity made it an ideal candidate for detecting planetary companions, leading to decades of intense observation and speculation. Although early claims of planets orbiting Barnard's star were later disproven, these efforts significantly advanced our planet-hunting techniques and technologies. The study of Barnard's star also contributed to our knowledge of stellar evolution. As one of the oldest known stars in our galaxy, estimated to be around 10 billion years old, it offers valuable insights into the life cycles of low-mass stars and the early history of our Milky Way. Its discovery and subsequent research have played a pivotal role in shaping modern astronomy and our quest to understand the universe around us. Barnard's star, one of our closest stellar neighbors, has been a subject of intense astronomical interest and debate for over a century. In the 1960s, astronomer Peter van der Kamp claimed to have detected planetary companions orbiting this red dwarf star. His observations, based on minute wobbles in the star's position, sparked excitement in the scientific community and public alike. However, van der Kamp's findings soon became a source of controversy. Other astronomers, using more advanced techniques and equipment, were unable to replicate his results. This led to scrutiny of van der Kamp's methods and data analysis. Some researchers suggested that the observed wobbles might have been caused by changes in the telescope's optics rather than the gravitational influence of planets. The debate surrounding Barnard's star highlighted Barnard's star, the giant star on a collision course with our Sun. For centuries, we thought the night sky was calm, eternal stillness. But lurking in the darkness is Barnard's star, a cosmic wanderer racing through space. This unassuming red dwarf, just 6 light-years away, is no ordinary neighbor. It's moving fast, faster than any other star near us, charging forward at a staggering 31,000 miles per hour. Discovered in 1916 by astronomer E. Barnard, its speed shook the scientific world. In just 10,000 years, a blink in cosmic time, it will come dangerously close, brushing the edges of our solar system, stirring up the distant Oort cloud, and possibly sending comets raining inward. A quiet threat, hidden in plain sight. One day, this tiny star might reshape our corner of the galaxy. The question is, will we be ready? Barnard's star is a remarkable celestial object that has captured the attention of astronomers for over a century. Located just 6 light-years away from Earth, it is one of our closest stellar neighbors, surpassed in proximity only by the Alpha Centauri system. This red dwarf star is notably smaller and cooler than our Sun, with a mass about 1/6 that of our home star and a surface temperature of around 3,000 degrees Celsius. What makes Barnard's star truly fascinating is its rapid movement across our night sky. It exhibits the fastest proper motion of any known star, appearing to zip across the celestial sphere at a rate that would see it traverse the width of the full moon in a mere 180 years. This swift motion was first noticed by American astronomer Edward Emerson Barnard in 1916, hence its name. Despite its proximity and fame among astronomers, Barnard's star is too faint to be seen with the naked eye. Its dim nature is due to its classification as a red dwarf, the most common type of star in our galaxy. These stars are known for their longevity, and Barnard's star is no exception, with an estimated age of around 10 billion years, making it considerably older than our Sun. For decades, Barnard's star was thought to host planetary companions, sparking intense scientific debate and numerous observational campaigns. Recent studies have provided evidence for a super-Earth orbiting this ancient star, although confirmation of this exoplanet remains a subject of ongoing research. The star continues to be a prime target for exoplanet hunters and astrobiologists, given its proximity and the potential for habitable worlds around red dwarf stars. Barnard's star is one of our closest stellar neighbors, situated in the constellation of Ophiuchus. This red dwarf star lies just 6 light-years away from our solar system, making it the fourth nearest star to Earth after the 3 stars in the Alpha Centauri system. Barnard's star is not visible to the naked eye due to its small size and low luminosity. In galactic terms, Barnard's star is located in the Milky Way's Orion arm, the same spiral arm that houses our own solar system. It resides in what astronomers call the galactic thin disk, a region where most of the galaxy's star formation occurs. This placement puts Barnard's star relatively close to the galactic plane, the imaginary flat surface that runs through the center of our galaxy's disk. Interestingly, Barnard's star is not a stationary neighbor. It has the largest proper motion of any known star, meaning it appears to move faster across our sky than any other star. This rapid apparent movement is due to its close proximity to Earth and its high velocity relative to our solar system. Barnard's star is one of our closest stellar neighbors, residing a mere 6 light-years away from Earth. This proximity makes it the 4th closest known star system to our Sun, after the 3 stars in the Alpha Centauri system. Despite its nearness, Barnard's star is not visible to the naked eye due to its small size and low luminosity. As a red dwarf, Barnard's star is much smaller and cooler than our Sun. It has only about 16% of the Sun's mass and less than 1% of its brightness. This dim nature, combined with its close distance, has made Barnard's star a subject of great interest for astronomers studying nearby stellar objects. The star's proximity to Earth allows scientists to observe its movement across the night sky more easily than other, more distant stars. In fact, Barnard's star holds the record for the largest proper motion of any known star, appearing to move faster across the celestial sphere than any other star from our vantage point on Earth. This cosmic neighbor has been the focus of numerous studies, including searches for exoplanets. Recent observations have suggested the presence of a super-Earth orbiting Barnard's star, though this finding is still under scrutiny. The ongoing research into this nearby star system continues to provide valuable insights into the nature of red dwarfs and the potential for life-supporting planets around them. Barnard's star was first discovered in 1916 by American astronomer Edward Emerson Barnard. This red dwarf star caught the attention of astronomers due to its exceptionally high proper motion across the night sky. In fact, Barnard's star moves faster than any other known star relative to our solar system, covering a distance equal to the Moon's diameter every 180 years. Despite being one of our closest stellar neighbors at just under 6 light-years away, Barnard's star is not visible to the naked eye due to its small size and low luminosity. It is classified as a red dwarf, much smaller and cooler than our Sun, with only about 15% of the Sun's mass and less than 1,000th of its brightness. The discovery of Barnard's star marked a significant moment in astronomical history, as it helped astronomers better understand the diversity of stars in our galactic neighborhood. Its rapid motion across the sky has made it a valuable target for studying stellar properties and searching for potential exoplanets. Edward Emerson Barnard, an American astronomer, discovered the star that now bears his name in 1916. Barnard's star quickly gained fame in the astronomical community due to its unique characteristics. It boasts the fastest proper motion of any known star, meaning it appears to move across the night sky more rapidly than any other stellar object visible from Earth. This red dwarf star is located in the constellation Ophiuchus and is one of our closest stellar neighbors, sitting just under 6 light-years away from our solar system. Its proximity and high proper motion made it an object of great interest for astronomers studying nearby stars and their movements through space. Barnard's discovery was particularly impressive given the technological limitations of early 20th century astronomy. He used a telescope at Yerkes Observatory to detect the star's rapid motion, showcasing his exceptional observational skills. This find significantly contributed to our understanding of the local stellar neighborhood and helped refine techniques for measuring stellar distances and movements. The star has since been the subject of numerous studies and has played a role in the search for exoplanets, though no confirmed planets have been found orbiting it to date. Barnard's star remains a testament to the power of careful observation and the ongoing importance of studying even the seemingly unremarkable stars in our cosmic backyard. Barnard's star holds a special place in astronomical research due to its unique characteristics and proximity to our solar system. Located just 6 light-years away, it ranks as the 4th closest star to Earth, making it an ideal subject for detailed observation and study. This celestial neighbor first caught the attention of astronomers because of its exceptionally rapid motion across the night sky. Barnard's star exhibits the fastest proper motion of any known star, moving at a rate that would see it traverse the width of the full moon in a mere 180 years. This swift movement allowed astronomers to detect and measure it with remarkable precision, providing valuable data for understanding stellar dynamics. Barnard's star is also noteworthy for being a red dwarf, the most common type of star in our galaxy. Its study offers insights into the life cycles and behavior of these numerous yet often overlooked stellar objects. Despite its proximity, Barnard's star is too faint to be seen with the naked eye, highlighting the vast range of stellar brightnesses in our cosmic neighborhood. The star has been the subject of intense planet hunting efforts for decades. While early claims of planetary companions were later disproven, recent observations have suggested the presence of at least one super-Earth orbiting this ancient star. This discovery not only expands our understanding of planetary formation around different star types, but also brings the search for potentially habitable worlds closer to home. Barnard's star, one of our closest stellar neighbors, is a stark contrast to our Sun in both size and mass. This diminutive star is a red dwarf, belonging to a class of stars that are the most common in our galaxy. Despite its proximity, Barnard's star is invisible to the naked eye due to its small size and low luminosity. In terms of size, Barnard's star is significantly smaller than our Sun. Its radius is estimated to be only about 15 to 20% that of our Sun. To put this into perspective, if we were to replace our Sun with Barnard's star, it would appear as a small, faint red orb in our sky, providing far less light and heat to Earth. The mass of Barnard's star is also considerably less than that of our Sun. Astronomers estimate its mass to be roughly 14 to 17% of our Sun's mass. This low mass is typical for red dwarf stars, which are much cooler and less energetic than stars like our Sun. Despite its small size and low mass, Barnard's star has captured the attention of astronomers for decades. Its proximity to Earth and its high proper motion across our sky make it an intriguing subject for study, offering insights into the nature and evolution of the most abundant type of star in our universe. Barnard's star is a red dwarf, one of the most common types of stars in our galaxy. This small, cool star is much less massive and luminous than our Sun. Red dwarfs are known for their longevity, burning their fuel slowly and steadily over incredibly long periods of time. Located just 6 light-years away from Earth, Barnard's star is our 4th nearest stellar neighbor. Despite its proximity, it cannot be seen with the naked eye due to its low luminosity. This star has fascinated astronomers for over a century because of its rapid proper motion across the night sky, moving faster than any other known star relative to Earth. Barnard's star is estimated to be around 10 billion years old, making it considerably older than our Sun. Its age and stability make it an intriguing target for exoplanet searches, as any planets orbiting it would have had ample time to develop and potentially support life. Recent observations have suggested the presence of a super-Earth orbiting Barnard's star, although this finding is still debated among astronomers. The study of this nearby red dwarf continues to provide valuable insights into stellar evolution and the potential for habitable worlds around the most common stars in our universe. Barnard's star, one of our closest stellar neighbors, is an ancient resident of our galactic neighborhood. Astronomers estimate this dim red dwarf to be approximately 10 billion years old, making it more than twice the age of our Sun. This venerable star has been steadily burning since the early days of our Milky Way galaxy, witnessing countless cosmic events throughout its long existence. The age of Barnard's star is determined through a combination of observational data and stellar evolution models. Its low mass and cool temperature are indicative of its advanced age, as smaller stars like red dwarfs burn their fuel much more slowly and efficiently than larger stars. This slow burn rate allows them to remain stable for incredibly long periods, far outlasting their more massive counterparts. Despite its age, Barnard's star continues to be a subject of fascination for astronomers. Its proximity to Earth, at just about 6 light-years away, makes it an ideal target for studying the properties and behavior of old, low-mass stars. The star's advanced age also provides valuable insights into the early history of our galaxy and the processes of stellar formation and evolution over cosmic timescales. Barnard's star has earned its reputation as a runaway star due to its exceptionally rapid motion across our night sky. This small, dim red dwarf is racing through space at a staggering speed of about 140 kilometers per second relative to our Sun. To put this into perspective, it's moving fast enough to traverse the diameter of the full moon in a human lifetime. This swift movement is not just impressive in its speed, but also in its visibility. Barnard's star exhibits the largest proper motion of any known star, meaning it appears to shift its position against the background of more distant stars faster than any other stellar object we've observed. This rapid apparent movement was first detected by astronomer E. Barnard in 1916, hence the star's name. The cause of Barnard's star's high velocity is rooted in its age and history. Astronomers believe it to be one of the oldest stars in our galaxy, possibly nearly as old as the universe itself. Over its long lifetime, gravitational interactions with other stars and massive objects have likely accelerated it to its current breakneck pace. Despite its speed, Barnard's star is actually one of our closest stellar neighbors, located just about 6 light-years away from Earth. Its combination of proximity and high velocity makes it a unique and important object of study for astronomers seeking to understand stellar motion and the history of our galactic neighborhood. The discovery of Barnard's star is a fascinating tale of astronomical perseverance and keen observation. In the early 20th century, American astronomer Edward Emerson Barnard was meticulously studying photographic plates of the night sky. His careful examination revealed something extraordinary, a faint star that appeared to be moving rapidly across the celestial sphere. Barnard's discovery in 1916 was groundbreaking because this star, later named after him, exhibited the largest proper motion of any known star. Proper motion refers to the apparent movement of a star across the sky, as seen from Earth. The rapid motion of Barnard's star indicated that it was relatively close to our solar system. This proximity made Barnard's star an object of great interest to astronomers. At just 6 light-years away, it became known as the second closest star system to Earth, after the Alpha Centauri system. The star's nearness and its high proper motion provided valuable opportunities for scientists to study stellar properties and movement. Barnard's meticulous work and his discovery highlight the importance of patient, detailed observation in astronomy. His finding not only added a new member to our list of nearby stellar neighbors, but also opened up new avenues for studying low-mass stars and the dynamics of our local stellar environment. Barnard's star was discovered in 1916 by American astronomer Edward Emerson Barnard. He detected this faint red dwarf star through careful observation and comparison of photographic plates taken over time. Barnard noticed that one particular star was moving rapidly across the sky relative to other stars in its vicinity. This movement, known as proper motion, is the apparent change in position of a star as seen from Earth. Barnard's star has the fastest proper motion of any known star, moving about 10 arc-seconds per year. This is equivalent to the width of a human hair viewed from 66 feet away. The detection of Barnard's star was a significant achievement in early 20th century astronomy. It demonstrated the power of long-term, systematic observations and the importance of patience in astronomical research. The star's rapid motion across the sky also hinted at its close proximity to our solar system. Despite being one of our nearest stellar neighbors at just 6 light-years away, Barnard's star is not visible to the naked eye due to its low luminosity. Its discovery and subsequent study have provided valuable insights into the nature of red dwarf stars and the diversity of our galactic neighborhood. The initial observation of Barnard's star relied on relatively simple yet effective tools available to astronomers in the early 20th century. Edward Emerson Barnard, the American astronomer who discovered the star in 1916, primarily used a large refracting telescope at Yerkes Observatory in Wisconsin. This telescope, with its 40-inch diameter lens, was one of the most powerful instruments of its time, allowing Barnard to detect the faint red dwarf star despite its low luminosity. Barnard's observations were complemented by photographic plates which were crucial for recording and analyzing stellar positions and movements. These glass plates, coated with light-sensitive emulsions, captured images of the night sky over long exposure times. By comparing plates taken at different times, Barnard was able to detect the star's rapid proper motion across the celestial sphere. Precise timekeeping devices were also essential for these observations. Accurate clocks allowed astronomers to track the exact moments of stellar positions, which was crucial for measuring the star's movement over time. Additionally, Barnard likely used a blink comparator, a device that rapidly alternated between 2 photographic plates, making it easier to spot objects that had moved between exposures. These tools, though considered rudimentary by modern standards, were state-of-the-art at the time and allowed for the groundbreaking discovery of what would become known as the fastest-moving star in our night sky as seen from Earth. Barnard's star has been a subject of fascination for astronomers since its discovery in 1916 by American astronomer Edward Emerson Barnard. Initially, this red dwarf star caught attention due to its exceptionally high proper motion across the night sky, moving at a rate of 10 arc-seconds per year. This rapid movement indicated that Barnard's star was relatively close to our solar system, making it an ideal candidate for studying nearby stellar objects. In the 1960s, controversy arose when astronomer Peter van der Kamp claimed to have detected planetary companions orbiting Barnard's star. He based this conclusion on apparent wobbles in the star's motion, which he interpreted as gravitational influences from orbiting planets. However, subsequent studies and more advanced observational techniques failed to confirm these findings, and the scientific community eventually dismissed van der Kamp's planetary claims. The advent of more sophisticated detection methods in recent decades has significantly advanced our understanding of Barnard's star. High-precision radial velocity measurements and advanced data analysis techniques have allowed astronomers to probe its environment with unprecedented accuracy. These efforts culminated in the 2018 announcement of a candidate exoplanet orbiting Barnard's star. This potential planet, designated Barnard Star B, is believed to be a super-Earth with a mass about 3 times that of our planet, orbiting its host star every 233 days. While the existence of Barnard Star B still requires further confirmation, this discovery represents a significant milestone in our evolving understanding of this nearby stellar neighbor. It demonstrates how technological advancements and persistent scientific inquiry can reveal new insights about even well-studied celestial objects, constantly reshaping our knowledge of the cosmos. Edward Emerson Barnard, a renowned American astronomer, played a crucial role in the discovery and naming of Barnard's star. In 1916, while working at Yerkes Observatory, Barnard noticed a faint star with an exceptionally high proper motion. This means the star appeared to move rapidly across the night sky compared to other stars. Barnard's keen eye and meticulous observations led him to recognize this star as the fastest moving star known at that time. His discovery was particularly impressive given the technological limitations of early 20th century astronomy. Barnard used a technique called blink comparison, where he rapidly switched between photographic plates taken at different times to detect stellar movement. The star's rapid motion across the sky indicated its close proximity to our solar system. This proximity, combined with its high proper motion, made Barnard's star a subject of great interest in the astronomical community. As a result of his groundbreaking work, the star was named after him, cementing Edward Emerson Barnard's legacy in the annals of stellar astronomy. Barnard's discovery highlighted the importance of patient, detailed observation in astronomy and demonstrated that even in the modern era, individual astronomers could make significant contributions to our understanding of the cosmos. Barnard's star, discovered in 1916 by American astronomer Edward Emerson Barnard, revolutionized our understanding of stellar motion and nearby celestial objects. This red dwarf star, located just 6 light-years from Earth, captured the attention of astronomers due to its exceptionally high proper motion across the night sky. The discovery of Barnard's star provided astronomers with a unique opportunity to study a nearby stellar neighbor in great detail. Its proximity and rapid movement allowed scientists to measure its parallax with unprecedented accuracy, refining our methods for determining stellar distances. This breakthrough improved our understanding of the cosmic distance ladder, a crucial tool for measuring vast cosmic scales. Furthermore, Barnard's star became a prime target in the search for exoplanets. Its close proximity made it an ideal candidate for detecting planetary companions, leading to decades of intense observation and speculation. Although early claims of planets orbiting Barnard's star were later disproven, these efforts significantly advanced our planet-hunting techniques and technologies. The study of Barnard's star also contributed to our knowledge of stellar evolution. As one of the oldest known stars in our galaxy, estimated to be around 10 billion years old, it offers valuable insights into the life cycles of low-mass stars and the early history of our Milky Way. Its discovery and subsequent research have played a pivotal role in shaping modern astronomy and our quest to understand the universe around us. Barnard's star, one of our closest stellar neighbors, has been a subject of intense astronomical interest and debate for over a century. In the 1960s, astronomer Peter van der Kamp claimed to have detected planetary companions orbiting this red dwarf star. His observations, based on minute wobbles in the star's position, sparked excitement in the scientific community and public alike. However, van der Kamp's findings soon became a source of controversy. Other astronomers, using more advanced techniques and equipment, were unable to replicate his results. This led to scrutiny of van der Kamp's methods and data analysis. Some researchers suggested that the observed wobbles might have been caused by changes in the telescope's optics rather than the gravitational influence of planets. The debate surrounding Barnard's star highlighted the challenges of detecting exoplanets, especially with the technology available at the time. It also underscored the importance of reproducibility in scientific research. The controversy served as a valuable lesson for the astronomical community, prompting improvements in observational techniques and data analysis methods. Despite the setback, the search for planets around Barnard's star continued. Modern observations have revealed a possible super-Earth orbiting the star, though this finding remains under investigation. The ongoing studies of Barnard's star demonstrate how scientific understanding evolves through debate, skepticism, and technological advancement. Our ability to study Barnard's star has improved dramatically thanks to technological advancements in astronomy. Early observations relied on basic telescopes and photographic plates, limiting our understanding of this nearby stellar neighbor. However, the development of more sophisticated instruments has revolutionized our approach. Modern charge-coupled device cameras have greatly enhanced our ability to detect minute changes in the star's position and brightness. These digital sensors are far more sensitive than traditional photographic methods, allowing astronomers to gather precise data over extended periods. This improved accuracy has been crucial in refining our measurements of Barnard's star's proper motion and potential planetary companions. Space-based observatories have also played a significant role in advancing our knowledge. Telescopes like Hubble and Gaia, operating above Earth's atmosphere, provide unparalleled clarity and precision in their observations. These instruments have helped astronomers measure Barnard's star's distance, motion, and physical properties with unprecedented accuracy. Spectroscopic technology has evolved considerably, enabling us to analyze the star's composition and behavior in great detail. Advanced spectrographs can now detect subtle shifts in spectral lines, revealing information about the star's velocity, temperature, and even the presence of orbiting planets. This wealth of data has transformed our understanding of Barnard's star from a mere point of light to a complex, dynamic system worthy of continued study. Barnard's star has been a focal point of astronomical research for over a century, captivating scientists with its unique characteristics and potential for discovery. In 1916, American astronomer Edward Emerson Barnard first measured the star's large proper motion, revealing it to be the fastest-moving star in our night sky. This discovery marked the beginning of intense scientific interest in this nearby celestial neighbor. A significant milestone occurred in the 1960s when Dutch astronomer Peter van der Kamp claimed to have detected planets orbiting Barnard's star using astrometric measurements. This announcement generated considerable excitement in the astronomical community, as it would have been the first detection of exoplanets. However, subsequent studies in the 1970s and 80s failed to confirm these findings, and they were eventually attributed to systematic errors in the observational equipment. The search for planets around Barnard's star continued with improved technology and methods. In 2018, an international team of astronomers announced the discovery of a super-Earth candidate orbiting the star. This planet, designated Barnard's star B, was detected using the radial velocity method, which measures tiny wobbles in the star's motion caused by an orbiting planet's gravitational pull. Most recently, observations using the Hubble Space Telescope and other advanced instruments have allowed astronomers to refine our understanding of Barnard's star's properties, including its mass, radius, and composition. These ongoing studies continue to provide valuable insights into the nature of red dwarf stars and the potential for habitable worlds around our stellar neighbors. Barnard's star has captivated astronomers and the public alike since its discovery in 1916 by American astronomer Edward Emerson Barnard. Initially, this red dwarf star garnered attention due to its status as the second closest star system to our Sun after the Alpha Centauri system. In the 1960s, interest in Barnard's star surged when astronomer Peter van der Kamp claimed to have detected planets orbiting it. This announcement sparked excitement about the possibility of nearby exoplanets and potential for extraterrestrial life. However, subsequent observations failed to confirm these findings, leading to a period of disappointment and decreased public attention. The star regained prominence in recent years with advancements in exoplanet detection technology. In 2018, astronomers announced the discovery of a super-Earth orbiting Barnard's star, reigniting public fascination. This finding not only validated the star's importance in astronomical research, but also rekindled hopes for potentially habitable worlds in our cosmic neighborhood. Today, Barnard's star continues to be a subject of intense study and public interest. Its proximity to Earth makes it an ideal target for future space exploration missions and a key focus in the search for exoplanets. As our understanding of this nearby stellar neighbor grows, so does its significance in both scientific circles and popular imagination. Barnard's star is classified as a red dwarf, specifically falling under the spectral type M4. This classification tells us a great deal about the star's characteristics. Red dwarfs are the most common type of star in our galaxy, but they're also among the smallest and coolest. Barnard's star, with its M4 designation, is on the smaller and cooler end of even this diminutive category. The star's reddish hue, which gives it its red dwarf moniker, is a direct result of its relatively cool surface temperature. While our Sun blazes at nearly 6,000 degrees Celsius, Barnard's star is a much milder 3,000 degrees. This proximity, combined with its unique characteristics, makes it an invaluable subject for studying the life cycles and behavior of the most numerous stars in our universe. Barnard's star, one of our closest stellar neighbors, is significantly cooler than our Sun. While our Sun blazes at a surface temperature of about 5,700 kelvins, Barnard's star is much chillier, with a surface temperature of only about 3,100 kelvins. This substantial difference in temperature is due to Barnard's star being a red dwarf, a class of stars that are smaller and less massive than our Sun. The cooler temperature of Barnard's star results in it emitting most of its light in the red and infrared parts of the spectrum, unlike our Sun, which emits strongly across the visible spectrum. This is why Barnard's star appears distinctly reddish when observed through telescopes. Despite being one of the closest stars to our solar system, its dimness makes it invisible to the naked eye from Earth. The lower temperature of Barnard's star also means it's much less luminous than our Sun. In fact, it emits only about 4/10,000ths as much energy as the Sun. This dramatic difference in energy output has significant implications for any potential planets orbiting Barnard's star, as the habitable zone where liquid water could exist would be much closer to the star than in our solar system. Barnard's star, one of our closest stellar neighbors, is a small and dim red dwarf star located approximately 6 light-years from Earth. Despite its proximity, determining its exact size has been a challenge for astronomers due to its faintness and small angular diameter. Recent measurements using advanced interferometric techniques have allowed scientists to estimate the radius of Barnard's star with greater precision. The current best estimate places its radius at about 20% that of our Sun. To put this into perspective, if we were to replace our Sun with Barnard's star, it would appear roughly 5 times smaller in our sky. This diminutive size is typical for red dwarf stars, which are the most common type of star in our galaxy. These stars are much cooler and less massive than our Sun, with Barnard's star having a surface temperature of around 3,100 Kelvin compared to the Sun's 5,700 Kelvin. The small size of Barnard's star contributes to its extremely long lifespan. While our Sun is expected to exist for about 10 billion years, Barnard's star may continue shining for trillions of years, making it one of the oldest stars in the universe. Barnard's star stands out as one of the smallest known stars in our Milky Way galaxy. This diminutive celestial body is a red dwarf, a class of stars that are inherently less massive and cooler than our Sun. In fact, Barnard's star has only about 16% of the Sun's mass, making it a true cosmic lightweight. To put this into perspective, if we were to line up 100 average stars from our galaxy, Barnard's star would be smaller than 95 of them. Its tiny size is a key factor in its longevity, as smaller stars burn through their fuel much more slowly than their larger counterparts. Despite its small stature, Barnard's star plays a significant role in astronomical research. Its proximity to Earth, combined with its low mass, makes it an ideal candidate for studying the properties of red dwarf stars, which are the most common type of star in our galaxy. Interestingly, while Barnard's star is considerably less massive than most stars we observe, it still outweighs many other celestial objects. It is several dozen times more massive than gas giant planets like Jupiter and thousands of times more massive than Earth. This comparison highlights the vast range of masses found among celestial bodies in our cosmic neighborhood. Barnard's star, one of our closest stellar neighbors, is a fascinating subject in the realm of astronomy. This dim red dwarf, located just 6 light-years away from Earth, has a luminosity that is remarkably low compared to our Sun. In fact, Barnard's star emits only about 1/2000th of the energy that our Sun does. This incredibly low luminosity means that despite its proximity to Earth, Barnard's star is not visible to the naked eye. It requires a telescope to observe, which is quite remarkable considering how close it is to us in cosmic terms. The star's faintness is due to its small size and cool temperature, typical characteristics of red dwarf stars. The low energy output of Barnard's star has intriguing implications for potential planetary systems around it. Any planets orbiting this star would need to be much closer to receive the same amount of energy that Earth gets from the Sun. This proximity could lead to interesting scenarios for potential life, as these planets would be more susceptible to stellar flares and radiation. Studying low-luminosity stars like Barnard's star helps astronomers understand the diversity of stellar objects in our galaxy and provides valuable insights into stellar evolution and the potential for life around different types of stars. Barnard's star, a small red dwarf located just 6 light-years from Earth, differs significantly from our Sun in its composition. This ancient star, estimated to be around 10 billion years old, contains far fewer heavy elements compared to our younger, middle-aged Sun. The most striking difference lies in the star's metallicity, which astronomers use to describe the abundance of elements heavier than hydrogen and helium. Barnard's star has a much lower metallicity than our Sun, with only about 10 to 20% of the heavy elements found in our star. This low metal content is a telltale sign of its age, as it formed when the universe contained fewer heavy elements. Another key difference is the abundance of specific elements. For instance, Barnard's star has lower levels of iron, carbon, and oxygen compared to our Sun. These elements play crucial roles in stellar evolution and planet formation, suggesting that any planets orbiting Barnard's star might have very different compositions from those in our solar system. The unique composition of Barnard's star affects its appearance and behavior. Its reddish hue and cooler temperature are direct results of its elemental makeup, making it a fascinating subject for astronomers studying stellar evolution and the early universe. Barnard's star, one of our closest stellar neighbors, is estimated to be around 10 billion years old. This venerable age places it among the oldest known stars in our galaxy, a true cosmic elder. Determining the age of stars is a complex process that relies on several methods and observations. For Barnard's star, astronomers have used a combination of techniques, including studying its composition, movement, and energy output. One key indicator of its age is the star's extremely low metallicity, which means it contains very few elements heavier than hydrogen and helium. This suggests that Barnard's star formed early in the universe's history, before many heavier elements were produced by previous generations of stars. Additionally, the star's slow rotation rate and low magnetic activity provide further evidence of its advanced age. As stars age, they tend to spin more slowly and become less magnetically active. The precise measurements of these properties in Barnard's star align with models of very old, low-mass stars, supporting the estimate of its ancient origins in the early days of our Milky Way galaxy. Barnard's star, one of our closest stellar neighbors, spins much more slowly than our Sun. While our Sun completes one rotation about its axis in approximately 25 days at its equator, Barnard's star takes a considerably longer time of around 130 days to complete a single rotation. This sluggish rotation is typical for older, smaller stars like Barnard's star. As stars age, they tend to slow down their spin due to a process called magnetic braking. Over billions of years, the star's magnetic field interacts with the charged particles it emits, gradually reducing its rotational speed. The slow rotation of Barnard's star has significant implications for its magnetic activity and potential habitability of any orbiting planets. Slower rotating stars generally have weaker magnetic fields and produce fewer stellar flares, which could create more stable conditions for potential life-bearing worlds. Interestingly, despite its slow rotation, Barnard's star still shows signs of stellar activity, including occasional flares. This challenges our understanding of the relationship between stellar rotation and activity, especially in older, low-mass stars, and continues to be a subject of ongoing research in stellar astrophysics. Barnard's star, one of our closest stellar neighbors at just 6 light-years away, has been the subject of intense scientific scrutiny for decades. Despite its proximity, our knowledge of its magnetic field remains limited. Astronomers have determined that Barnard's star is a red dwarf, significantly smaller and cooler than our Sun. These characteristics typically suggest the presence of a magnetic field, as red dwarfs often exhibit strong magnetic activity. Recent observations using advanced spectropolarimetric techniques have provided some insights into the magnetic properties of Barnard's star. Scientists have detected signs of a moderate magnetic field, though it appears to be weaker than those observed in many other red dwarfs. This relatively calm magnetic environment might be attributed to the star's advanced age, estimated to be around 10 billion years old. The magnetic field of Barnard's star is believed to play a crucial role in its stellar activity and potential habitability for any orbiting planets. While the star occasionally displays small flares, its magnetic field seems to contribute to a more stable stellar environment compared to younger, more volatile red dwarfs. This stability could have important implications for the potential development of life on any planets in its system. Understanding the magnetic field of Barnard's star not only provides valuable information about this particular celestial object, but also contributes to our broader knowledge of stellar magnetic fields and their evolution over time. As our observational techniques continue to improve, we may uncover more details about the intriguing magnetic properties of our diminutive stellar neighbor. Barnard's star stands out among red dwarfs for several notable characteristics. First, it is one of the closest stars to our solar system, located just 6 light-years away. This proximity has allowed astronomers to study it in great detail, revealing its unique properties. One of the most striking features of Barnard's star is its exceptionally high proper motion. It moves across the sky faster than any other star visible from Earth, covering a distance equal to the Moon's diameter every 180 years. This rapid movement is due to its close proximity and high velocity relative to our solar system. Barnard's star is also one of the oldest known stars in our galaxy, estimated to be between 7 and 12 billion years old. This advanced age contributes to its extremely low metallicity, meaning it has a much lower abundance of elements heavier than helium compared to younger stars like our Sun. Another intriguing aspect of Barnard's star is its variable nature. It exhibits small but detectable fluctuations in brightness, likely caused by star spots on its surface. These variations, combined with its age and composition, make Barnard's star a valuable target for studying stellar evolution and the long-term behavior of red dwarfs. Barnard's star, a red dwarf located just 6 light-years from Earth, holds the record for the fastest proper motion of any known star. This celestial speedster appears to race across our sky at an astonishing rate of 10.5 arcseconds per year. To put this into perspective, it would take only 180 years for Barnard's star to traverse a distance in our sky equal to the diameter of the full moon. This rapid movement is not due to the star's actual velocity through space being exceptionally high. Rather, it is a result of its close proximity to Earth. Like a car passing nearby on a highway appears to move faster than a distant airplane, Barnard's star's closeness to us amplifies its apparent motion across our celestial sphere. Despite this swift proper motion, Barnard's star is actually moving towards our solar system. Its radial velocity, or the speed at which it is approaching us, is about 110 kilometers per second. This combination of lateral movement across our sky and its approach towards us creates a unique path when observed over time. Astronomers have been closely monitoring Barnard's star for over a century, making it an excellent subject for studying stellar motion and the dynamics of our local cosmic neighborhood. Its proper motion serves as a vivid reminder of the constant movement and change occurring in our seemingly static night sky. Barnard's star is racing through space at an impressive speed relative to our Sun. This small, dim red dwarf star is hurtling towards us at about 140 kilometers per second. To put this into perspective, that is roughly 313,000 miles per hour. This rapid motion makes Barnard's star the fastest moving star in our night sky as seen from Earth. The speed of Barnard's star is particularly notable because most stars in our galactic neighborhood move much more slowly relative to each other. Our Sun, for instance, orbits the center of the Milky Way at about 220 kilometers per second, but its motion relative to nearby stars is generally much less. This high-speed stellar neighbor was discovered in 1916 by American astronomer E. Barnard. Its rapid motion across our sky, known as proper motion, causes it to move the width of the full moon in about 180 years, a blink of an eye in cosmic terms. Despite its speed, we need not worry about a collision. Barnard's star is currently about 6 light-years away from us and will make its closest approach in about 10,000 years, coming within about 3.5 light-years of our solar system. Even at its closest, it will remain far too distant to have any significant gravitational effect on our planetary system. Barnard's star, a red dwarf located just 6 light-years from our solar system, is renowned for its rapid movement across the night sky. This swift apparent motion, known as proper motion, is primarily due to its close proximity to Earth combined with its high velocity through space. The star's closeness to our planet is a key factor. As one of our nearest stellar neighbors, even a relatively modest speed appears amplified from our vantage point. This effect is similar to how nearby cars on a highway seem to move faster than distant ones, even if they're traveling at the same speed. However, Barnard's star is not just close, it's also moving quickly. It hurtles through space at about 140 kilometers per second relative to the Sun. This high velocity is believed to be the result of the star's advanced age. Over billions of years, gravitational interactions with other stars and galactic structures have accelerated Barnard's star to its current speed. The combination of its proximity and velocity results in Barnard's star appearing to move across the sky at a rate of 10.3 arcseconds per year. To put this in perspective, it would take only about 180 years for the star to traverse a distance equal to the diameter of the full moon as seen from Earth. This remarkable proper motion makes Barnard's star a fascinating subject for astronomers and a unique feature of our local cosmic neighborhood. Barnard's star stands out among its stellar neighbors due to its exceptionally high velocity through space. This small, dim red dwarf is racing across the sky at a remarkable rate of 10.5 arcseconds per year, faster than any other known star relative to Earth. To put this into perspective, it would take only 180 years for Barnard's star to traverse a distance in the sky equal to the diameter of the full moon. This rapid motion is not just an illusion caused by its proximity to us. Barnard's star is actually moving through space at about 140 kilometers per second relative to the Sun. This is nearly 3 times faster than the average velocity of stars in our galactic neighborhood. Its high speed suggests that Barnard's star might be a visitor from the older, more distant parts of our Milky Way galaxy. The star's velocity has significant implications for our understanding of stellar dynamics and galactic structure. It provides valuable data for astronomers studying the movement and evolution of stars within our galaxy. Moreover, the rapid motion of Barnard's star has made it a prime target for exoplanet searches, as its movement across the sky can help reveal the presence of any orbiting planets through subtle wobbles in its path. Despite its speed, Barnard's star is currently one of our closest stellar neighbors, located just about 6 light-years away from Earth. However, its high velocity means this won't always be the case. In about 10,000 years, it will make its closest approach to our solar system, coming within about 3.5 light-years of the Sun, before continuing its journey and gradually increasing its distance from us. Barnard's star is racing towards our solar system at an impressive speed of about 30 miles per second. This red dwarf, located just 6 light-years away, is the fastest-moving star visible from Earth. Its rapid approach makes it a prime target for studying stellar motion and the dynamics of our galactic neighborhood. Despite its swift movement, there is no need for concern about a collision with our solar system. Even at its current velocity, Barnard's star will make its closest approach to the Sun in about 10,000 years, and even then, it will still be a comfortable distance of about 3.5 light-years away. The star's motion is not perfectly aligned with our solar system. It is moving in a diagonal path relative to us, which astronomers describe as having both radial velocity towards us and proper motion across our sky. This combination of movements causes Barnard's star to trace a curved path through space as seen from Earth. Interestingly, the rapid motion of Barnard's star allows astronomers to measure its distance with great precision using parallax. This technique, combined with its proximity and speed, makes Barnard's star an invaluable celestial object for calibrating our understanding of stellar distances and motions in the cosmos. Barnard's star has been a subject of intense astronomical study due to its rapid motion across the night sky. Astronomers have tracked this star's movement using a technique called astrometry, which involves precisely measuring the positions of celestial objects over time. The motion of Barnard's star was first detected in 1916 by American astronomer Edward Emerson Barnard. He noticed that the star was moving unusually quickly relative to other stars in the sky. This rapid movement is known as proper motion, and Barnard's star exhibits the largest known proper motion of any star visible from Earth. Over the years, astronomers have used increasingly sophisticated instruments to measure the star's position. Early observations relied on photographic plates, where images of the star were captured on glass plates coated with light-sensitive emulsion. By comparing plates taken years apart, scientists could track the star's movement across the celestial sphere. Modern measurements employ advanced technologies such as charge-coupled device cameras and space-based telescopes. These tools allow for incredibly precise measurements of Barnard's star's position, enabling astronomers to detect even minute changes in its motion. This ongoing observation has revealed not only the star's proper motion, but also its parallax, which helps determine its distance from Earth and potential wobbles that might indicate the presence of orbiting planets. Barnard's star, the fastest-moving star in our night sky, offers astronomers a unique window into stellar dynamics. Its rapid proper motion across the celestial sphere, covering a distance equal to the Moon's diameter every 180 years, allows scientists to study stellar movement with unprecedented detail. This swift movement provides valuable data on the velocities of nearby stars and helps refine our models of galactic structure. By observing Barnard's star, astronomers can better understand how stars interact with the gravitational forces of our galaxy, shedding light on the complex dance of celestial bodies within the Milky Way. Furthermore, the high velocity of Barnard's star relative to our solar system suggests it might be part of an older population of stars. This insight helps astronomers piece together the history of our galactic neighborhood and provides clues about star formation and evolution in the early stages of our galaxy's life. The study of Barnard's star's motion also contributes to our understanding of proper motion and parallax measurements, crucial techniques in determining stellar distances. These refined methods improve our ability to map the three-dimensional structure of our cosmic surroundings, enhancing our overall grasp of stellar dynamics and galactic architecture. Barnard's star, one of our closest stellar neighbors, exhibits a significant radial velocity that greatly influences our observations. This rapid motion through space, directed along our line of sight, causes the star's light to shift towards the red end of the spectrum. This phenomenon, known as redshift, occurs as the star moves away from Earth at a speed of about 30 kilometers per second. The high radial velocity of Barnard's star has made it a prime target for exoplanet hunters. As the star moves, any planets orbiting it would cause tiny wobbles in its motion. These wobbles can be detected through precise measurements of the star's radial velocity, allowing astronomers to infer the presence of unseen companions. Moreover, the fast proper motion of Barnard's star across the night sky, combined with its radial velocity, provides astronomers with a unique opportunity to study stellar kinematics. By tracking its movement over time, scientists can better understand the dynamics of stars in our galactic neighborhood and refine models of stellar evolution. The radial velocity of Barnard's star also serves as a valuable calibration tool for astronomical instruments. Its consistent and well-measured motion allows researchers to check the accuracy of their velocity measurements, ensuring the reliability of data collected on other celestial objects. Barnard's star, one of our closest stellar neighbors, has a parallax of about 0.55 arcseconds. This measurement is crucial in determining the star's distance from Earth, which turns out to be approximately 6 light-years away. Parallax is measured by observing the apparent shift in a star's position against the background of more distant stars as Earth orbits the Sun. Astronomers take precise measurements of the star's position at different times of the year, typically 6 months apart when Earth is on opposite sides of its orbit. The tiny angle of this apparent shift is the parallax. For Barnard's star, this shift is relatively large compared to most stars, making it easier to measure accurately. The larger parallax is due to its proximity to our solar system. Astronomers use sophisticated telescopes and imaging equipment to detect these minute changes in position, often employing charge-coupled devices to capture highly detailed images of the star field. The parallax measurement of Barnard's star has been refined over time, with space-based observatories like the European Space Agency's Gaia mission providing extremely precise data. This ongoing improvement in measurement techniques allows astronomers to continually refine our understanding of our stellar neighborhood and the broader cosmos. Our ability to measure Barnard's star's motion has dramatically improved since its discovery in 1916 by Edward Emerson Barnard. Initially, astronomers relied on photographic plates to track the star's position against background stars over time. This method, while groundbreaking for its era, was limited by the resolution of photographic equipment and human measurement errors. The advent of charge-coupled devices, or CCDs, in the 1970s revolutionized astronomical measurements. These electronic light sensors provided much higher precision and sensitivity than photographic plates, allowing for more accurate tracking of Barnard's star's proper motion and parallax. In recent decades, space-based telescopes have taken our measurements to new heights. The European Space Agency's Hipparcos mission, operational in the 1990s, significantly improved our understanding of Barnard's star's distance and motion. This was followed by the Gaia mission, launched in 2013, which has provided unprecedented accuracy in measuring stellar positions and motions. Today, we can measure Barnard's star's proper motion with an accuracy down to milliarc seconds per year, a level of precision that would have been unimaginable to early 20th century astronomers. This improved accuracy has allowed us to better understand not only Barnard's star itself, but also the dynamics of our local stellar neighborhood. Barnard's star holds a significant place in our cosmic neighborhood. It ranks as the 4th closest star system to our Sun, following the 3 stars of the Alpha Centauri system. This red dwarf star sits just 6 light-years away from Earth, making it a relatively close neighbor in the vastness of space. Despite its proximity, Barnard's star is not visible to the naked eye due to its dim nature. It's a small, cool star with only about 16% of the Sun's mass and less than 1% of its brightness. This combination of closeness and low luminosity has made Barnard's star a subject of great interest to astronomers. The star's nearness to our solar system allows scientists to study it in detail, providing valuable insights into the characteristics and behavior of red dwarf stars, which are the most common type of star in our galaxy. Barnard's star also exhibits an exceptionally high proper motion across the sky, moving at a rate that would see it travel the width of the full moon in about 180 years. This nearby stellar neighbor serves as an important target for exoplanet searches and studies of stellar evolution, helping us better understand the diversity of star systems in our local cosmic environment. Its proximity makes it a prime candidate for future interstellar exploration missions, should such technologies ever become feasible. Barnard's star currently holds the position of the second closest star system to Earth, but this hasn't always been the case. The cosmic dance of stars through the galaxy means that stellar neighborhoods are constantly changing, albeit on timescales of thousands or millions of years. Approximately 10,000 years ago, Barnard's star was not even among the top 10 closest stars to our solar system. Its rapid proper motion, one of the highest observed for any star, has been bringing it closer to Earth over time. This motion will continue, and Barnard's star is expected to make its closest approach to our solar system in approximately 10,000 years from now. Interestingly, other stars have held the title of second closest in the past. For instance, about 70,000 years ago, a small red dwarf called Schultz's star passed through the outer reaches of our solar system, briefly becoming one of our closest stellar neighbors. It has since moved away and is no longer considered a nearby star. The dynamic nature of stellar movements means that our cosmic neighborhood is ever-changing. While Proxima Centauri currently holds the title of closest star to Earth, and Barnard's star is the runner-up, this cosmic leaderboard will continue to evolve over vast spans of time, reshuffling the stars in our vicinity. Barnard's star, the closest single star to our solar system after the Alpha Centauri system, is currently about 6 light-years away from Earth. This red dwarf star is moving rapidly across our sky, covering a distance equal to the Moon's diameter every 180 years. Despite this swift motion, Barnard's star will remain one of our closest stellar neighbors for thousands of years to come. The star's trajectory will bring it even closer to our solar system over time. Calculations show that Barnard's star will make its closest approach to the Sun in approximately 10,000 years. At that point, it will be just under 5.5 light-years away, slightly closer than it is now. After this close encounter, Barnard's star will begin to move away from us again. However, the process of it becoming significantly more distant will be gradual. It will take tens of thousands of years before Barnard's star is no longer considered one of the closest stars to Earth. This relatively stable proximity over human timescales allows astronomers to study Barnard's star in detail, making it an important target for exoplanet searches and investigations into the properties of red dwarf stars. Its consistent closeness provides a valuable window into the nature of the most common type of star in our galaxy. Barnard's star, as the 4th closest star system to our Sun, holds significant importance for astronomical research. Its proximity, just 6 light-years away, allows scientists to study it in exceptional detail, providing valuable insights into stellar evolution and behavior. This red dwarf star serves as an ideal target for exoplanet searches. Its closeness makes it easier to detect subtle wobbles or dips in brightness that might indicate orbiting planets. In fact, astronomers have already discovered a super-Earth-sized planet in its orbit, highlighting the potential for further discoveries in nearby star systems. Barnard's star also exhibits an unusually high proper motion, moving across our sky faster than any other known star. This rapid movement allows researchers to study stellar motion and galactic structure with unprecedented precision. By tracking its path over time, scientists can better understand the dynamics of our local stellar neighborhood and refine models of galactic evolution. Furthermore, as one of the oldest known stars in our galaxy, Barnard's star offers a unique window into the early universe. Studying its composition and characteristics helps astronomers piece together the history of star formation in the Milky Way, shedding light on the processes that have shaped our cosmic environment over billions of years. Barnard's star, as the second closest star system to our own, offers astronomers a unique opportunity for detailed observation. Its nearness to Earth, at just under 6 light-years away, allows us to study it with exceptional clarity and precision. This proximity means that even small telescopes can detect its motion and properties, making it an accessible target for both professional and amateur astronomers. The star's closeness also amplifies the effects of its movement through space. Barnard's star exhibits the largest proper motion of any known star, appearing to move across our sky faster than any other stellar object. This rapid apparent motion, first noted by astronomer E. Barnard in 1916, has allowed scientists to accurately measure its velocity and trajectory. Furthermore, the star's proximity enables us to detect subtle changes in its position caused by potential orbiting planets. This has led to the discovery of a candidate exoplanet, Barnard's star B, although its existence is still debated. The ability to potentially study a planetary system around our stellar neighbor provides invaluable insights into planetary formation and evolution. However, the brightness of Barnard's star poses some challenges. Despite being so close, it is a dim red dwarf, much fainter than our Sun. This low luminosity actually makes it difficult to study using certain techniques that rely on analyzing a star's light. Nevertheless, its proximity more than compensates for this, allowing astronomers to gather data that would be impossible to obtain from more distant stars. Having a close stellar neighbor like Proxima Centauri offers several exciting possibilities for scientific exploration and potential future space travel. The proximity of this star system, at just over 4 light-years away, makes it an ideal target for detailed study using our most advanced telescopes and instruments. This close observation allows astronomers to gather precise data about the star's composition, behavior, and any planets orbiting it. The discovery of Proxima Centauri b, an Earth-sized planet in the habitable zone of its star, has sparked great interest in the scientific community. This planet provides a unique opportunity to study a potentially habitable world outside our solar system. By analyzing its atmosphere and other characteristics, we might gain valuable insights into the conditions necessary for life to exist on other planets. From a space exploration perspective, Proxima Centauri represents our best chance for interstellar travel in the foreseeable future. Its relative closeness makes it a more realistic target for advanced propulsion technologies that might be developed in the coming decades. Sending probes or even crewed missions to this nearby star system could provide unprecedented data about other stellar environments and greatly expand our understanding of the universe. Furthermore, studying Proxima Centauri and its planetary system can help us better understand the diversity of star systems in our galaxy. By comparing it to our own solar system, scientists can refine theories about planetary formation and evolution, potentially shedding light on the uniqueness or commonality of Earth-like worlds in the cosmos. Barnard's star is the second closest star system to our Sun, following the Alpha Centauri system. While Alpha Centauri is approximately 4.37 light-years away from Earth, Barnard's star is slightly farther at about 6 light-years distant. This relatively small difference in cosmic terms means that both star systems are practically in our stellar backyard. Despite being our second nearest neighbor, Barnard's star is not visible to the naked eye due to its low luminosity. It is a small, cool red dwarf star, much dimmer than the stars in the Alpha Centauri system. In contrast, Alpha Centauri A and B are bright, sun-like stars that can be seen without a telescope from the southern hemisphere. The proximity of these stars offers astronomers unique opportunities to study stellar systems up close. Barnard's star, in particular, has been a subject of intense scientific interest due to its high proper motion across the sky, which is faster than any other known star. This rapid movement, combined with its closeness, makes it an excellent target for studying stellar dynamics and searching for exoplanets. Both Barnard's star and the Alpha Centauri system continue to captivate scientists and space enthusiasts alike, serving as stepping stones in our understanding of the local stellar neighborhood and potential targets for future interstellar exploration. Studying our nearest star, the Sun, presents unique challenges despite its proximity to Earth. Its intense brightness overwhelms most astronomical instruments designed for observing distant, fainter stars. This forces scientists to develop specialized equipment and techniques to safely examine our home star. The Sun's powerful radiation and magnetic fields also create obstacles. These phenomena interfere with observations and can damage sensitive instruments if not properly shielded. Solar flares and coronal mass ejections pose risks to both ground-based and space-based observatories, requiring constant monitoring and protective measures. Paradoxically, the Sun's closeness can make it difficult to observe as a whole. Its large apparent size in our sky means that capturing a complete image of the Sun often requires multiple observations stitched together. This process can be time-consuming and may miss rapid changes occurring across the solar surface. Furthermore, the Sun's dynamic nature complicates long-term studies. Features on its surface evolve quickly, sometimes within minutes or hours. This rapid change makes it challenging to track specific phenomena over extended periods and requires continuous observation to fully understand solar processes. Barnard's star has captured the public imagination as one of our closest stellar neighbors, sparking widespread interest in astronomy and the search for exoplanets. Located just 6 light-years away, this dim red dwarf star is the 4th closest star system to our Sun, making it an enticing target for both professional astronomers and amateur stargazers. The star's rapid proper motion across the night sky, the fastest of any known star, has made it a favorite subject for observers. This movement, first noted by Edward Emerson Barnard in 1916, allows people to witness cosmic change within a human lifetime, bringing the dynamic nature of the universe into tangible reality. Barnard's star has also played a significant role in the hunt for exoplanets. For decades, astronomers believed they had detected planets orbiting the star, fueling excitement about potential alien worlds in our cosmic backyard. Although these early claims were later disproven, they sparked crucial debates about planet detection methods and inspired improvements in observational techniques. More recently, the confirmed discovery of an exoplanet orbiting Barnard's star in 2018 reignited public interest. This finding not only validated the star's importance in astronomical research, but also reinforced the idea that planets may be common around red dwarf stars, the most numerous stellar type in our galaxy. This discovery has further motivated both professional and amateur astronomers to continue their exploration of our stellar neighborhood, fostering a deeper connection between the public and the cosmos. Barnard's star, as one of our closest stellar neighbors, presents a wealth of exciting research opportunities for astronomers and astrophysicists. Its proximity, just 6 light-years away, allows for detailed observations that are challenging or impossible with more distant stars. One of the most promising avenues for future research is the search for exoplanets. While a super-Earth has already been detected orbiting Barnard's star, continued observations could reveal additional planets in the system. The star's closeness enables scientists to use multiple detection methods, including radial velocity measurements and direct imaging techniques, to search for smaller, potentially habitable worlds. The star's age and composition also make it an excellent target for studying stellar evolution. As an ancient red dwarf, Barnard's star provides insights into the long-term behavior and life cycles of the most common type of star in our galaxy. Detailed spectroscopic analysis could reveal more about its chemical makeup and how it has changed over billions of years. Furthermore, Barnard's star's high proper motion across the sky offers unique opportunities to study stellar kinematics and galactic structure. By precisely measuring its movement and combining this data with observations of other nearby stars, scientists can refine our understanding of the Milky Way's shape, size, and evolution. This research could also contribute to improved models of stellar populations and galactic dynamics. Barnard's star, one of our nearest stellar neighbors, has captured the attention of astronomers for decades due to its rapid motion across our night sky. This red dwarf, located just 6 light-years away, is moving towards our solar system at a speed of about 140 kilometers per second. However, contrary to some misconceptions, Barnard's star is not on a direct collision course with our Sun. The evidence actually suggests that Barnard's star will make its closest approach to our solar system in about 10,000 years. At that point, it will come within about 3.5 light-years of the Sun, which is still an enormously vast distance. After this close encounter, Barnard's star will continue its journey, moving away from our solar system. The perception of a potential collision stems from the star's high proper motion, which is the apparent movement of a star against the background of more distant stars. Barnard's star has the highest proper motion of any known star, covering a distance equal to the Moon's diameter every 350 years. This rapid movement, combined with its approach towards us, can create the illusion of an impending collision. Astronomers have accurately measured the trajectory of Barnard's star using various methods, including parallax measurements and spectroscopic observations. These precise calculations confirm that while the star is indeed approaching our solar system, it will safely pass by without any risk of collision. The star's path serves as a reminder of the dynamic nature of our galaxy, where stars are in constant motion, occasionally passing near one another, but rarely, if ever, actually colliding. Barnard's star has long fascinated astronomers due to its rapid motion across our night sky. As the fastest moving star visible from Earth, its trajectory has been studied extensively. The predictions of Barnard's star's path through space have become increasingly accurate over time, thanks to advancements in observational techniques and technology. Modern measurements using high-precision instruments have refined our understanding of Barnard's star's proper motion and radial velocity. These observations have allowed astronomers to calculate its trajectory with remarkable accuracy. The star's position can now be predicted with a margin of error of just a few milliarc seconds, which is an incredibly small angular measurement in astronomical terms. However, it's important to note that even the most precise measurements have some degree of uncertainty. Over very long timescales, small errors can accumulate, potentially affecting long-term predictions. Additionally, factors such as the gravitational influence of nearby stars or undiscovered planets orbiting Barnard's star could slightly alter its path in ways that are difficult to account for in current models. Despite these potential sources of error, the predictions of Barnard's star's trajectory remain highly reliable for the foreseeable future. Astronomers continue to refine their measurements and models, ensuring that our understanding of this nearby stellar neighbor becomes ever more precise. Barnard's star, one of our nearest stellar neighbors, is steadily moving towards our solar system. This red dwarf star, located just 6 light-years away, is currently the fastest-moving star in our night sky as seen from Earth. Its rapid proper motion was first discovered by astronomer E. Barnard in 1916. Despite its speedy approach, Barnard's star won't reach its closest point to our solar system for quite some time. Astronomers predict that it will make its nearest approach in approximately 10,000 years. At that time, it will come within about 3.5 light-years of our Sun, briefly taking the title of our closest stellar neighbor from the Alpha Centauri star system. This cosmic encounter, while closer than our current nearest stars, won't pose any threat to Earth or our solar system. Even at its closest, Barnard's star will remain far too distant to have any gravitational influence on our planets or disturb the Oort cloud, the sphere of icy bodies that surrounds our solar system. After this close approach, Barnard's star will continue its journey through space, gradually moving away from us once again. This stellar passerby offers astronomers a unique opportunity to study the long-term movement and behavior of nearby stars, contributing to our understanding of stellar dynamics in our local cosmic neighborhood. Barnard's star, one of our closest stellar neighbors, is on a trajectory that will bring it even nearer to our solar system in the distant future. Astronomers have calculated that its closest approach to our Sun will occur in approximately 60,000 years. At that time, Barnard's star is expected to come within about 3.5 light years of our solar system. This cosmic encounter, while closer than Barnard's star's current position, still keeps it at a vast distance by human standards. To put this into perspective, even at its closest approach, Barnard's star will remain farther from us than our current nearest stellar neighbor, Proxima Centauri, which lies about 4.25 light years away. Despite this enormous distance, the close passage of Barnard's star will make it the brightest red dwarf visible in Earth's night sky. This event serves as a reminder of the dynamic nature of our galaxy, where stars are in constant motion, slowly altering the cosmic landscape over millennia. Barnard's star, a red dwarf located just 6 light years from Earth, is one of our closest stellar neighbors. Despite its proximity, this dim star poses no immediate threat to our solar system. Barnard's star is actually moving towards us at a rapid pace, covering a distance of about 90 kilometers per second. This motion will bring it even closer to our solar system in the coming millennia. However, the effects of this approach on our solar system will be minimal. Even at its closest point, which will occur in approximately 10,000 years, Barnard's star will still be about 3.5 light years away from us. This distance is far too great to cause any significant gravitational disturbances to the planets orbiting our Sun. The most noticeable change will be in our night sky. As Barnard's star draws nearer, it will gradually become brighter. At its closest approach, it might be visible to the naked eye, appearing as a faint, reddish point of light. This would add a new star to our familiar constellations, albeit temporarily on cosmic timescales. While Barnard's star's approach is an interesting astronomical event, it serves more as a reminder of the dynamic nature of our galaxy than as a cause for concern. The vast distances between stars in our cosmic neighborhood ensure that such close encounters, while fascinating, rarely have any substantial impact on planetary systems like our own. Barnard's star, the fourth closest star system to our Sun, is too distant to exert any significant gravitational influence on our planets. At approximately 6 light years away, its gravitational pull is negligible compared to the dominant forces within our solar system. The Sun's immense mass overshadows any external gravitational effects on our planets. Even Jupiter, the largest planet in our solar system, has a minimal impact on Earth's orbit. The influence of a star as small as Barnard's star, which is only about 1/6 the mass of our Sun, is even less consequential at such a great distance. While Barnard's star is notable for its high proper motion across our sky, this movement does not translate to gravitational effects on our solar system. Its rapid apparent motion is due to its relative closeness to Earth and its high velocity through space, not because of any direct interaction with our planets. In the realm of stellar neighbors, closer stars like Alpha Centauri might have slightly more influence, but even their effects are imperceptible on the scale of our planetary orbits. The stability of our solar system is primarily governed by the Sun and the complex interactions among the planets themselves. Barnard's star, the fastest moving star in our night sky, is steadily approaching our solar system. As it draws nearer over the next tens of thousands of years, its gravitational influence could have significant effects on the outer reaches of our solar system, particularly the Oort cloud. The Oort cloud is a vast, spherical shell of icy bodies that surrounds our solar system, extending nearly a light year from the Sun. These objects, primarily composed of frozen water, methane, and carbon dioxide, are loosely held in their orbits by the Sun's gravity. The approach of Barnard's star could potentially disrupt this delicate balance. As Barnard's star moves closer, its gravitational pull might cause some Oort cloud objects to be nudged out of their current orbits. This could result in a few different scenarios. Some objects might be pulled inward, potentially increasing the number of long-period comets entering the inner solar system. Others might be ejected from the solar system entirely, becoming interstellar wanderers. However, it's important to note that these effects would occur over extremely long timescales and would likely be subtle. The vast distances involved mean that even as Barnard's star makes its closest approach, its influence on the Oort cloud will be gradual and limited. Nonetheless, this stellar pass-by serves as a reminder of the dynamic nature of our cosmic neighborhood and the long-term processes that shape our solar system. Barnard's star, the fourth closest star system to our Sun, is steadily approaching our solar system. Despite its proximity, the effects on Earth during its closest approach will be minimal. Barnard's star is a small, dim red dwarf, only about 1/6 the mass of our Sun. Its relatively low mass means its gravitational influence on our solar system will be negligible. At its closest approach, estimated to occur in approximately 10,000 years, Barnard's star will still be about 3.5 light-years away from Earth. This distance is vast on human scales, equivalent to over 30 trillion kilometers. Even at this closest point, Barnard's star will not be visible to the naked eye from Earth due to its low luminosity. The star's approach will not disrupt the orbits of planets in our solar system or cause any significant changes to Earth's climate or environment. It will, however, provide astronomers with an excellent opportunity to study a nearby star system in greater detail. This could potentially yield valuable insights into the nature of red dwarf stars, which are the most common type of star in our galaxy. While the physical consequences for Earth will be negligible, the closest approach of Barnard's star might have broader implications for human civilization, depending on our technological advancement at that time. It could serve as a target for interstellar exploration or communication efforts, opening up new possibilities for scientific discovery and potentially expanding our understanding of the cosmos. The collision course between our Milky Way galaxy and the Andromeda galaxy is a cosmic dance that will unfold over an incredibly long timescale. This galactic encounter is expected to begin in about 4 billion years and will continue for several billion years more. The initial approach and first close pass will take roughly 2 billion years. During this time, the two galaxies will interact gravitationally, distorting each other's shapes and triggering bursts of star formation. After the first close approach, the galaxies will move apart again, only to be drawn back together by their mutual gravitational attraction. This process of coming together and moving apart will repeat several times over the course of about 2 billion years. With each pass, the galaxies will become more entangled and distorted, gradually merging into a single, larger elliptical galaxy. The entire process, from the beginning of the collision to the final settling of the new merged galaxy, is estimated to take between 4 and 5 billion years. This time frame is so vast that it exceeds the current age of the Earth. By the time the collision is complete, our Sun will have already exhausted its hydrogen fuel and expanded into a red giant, fundamentally altering the solar system. It is worth noting that despite the term collision, individual stars within the galaxies are unlikely to physically collide due to the vast distances between them. Instead, the collision refers to the overall mixing and merging of the two galactic systems, resulting in a transformed cosmic landscape that future observers would scarcely recognize as our once separate galaxies. Predicting the future path of Barnard's star presents several challenges for astronomers. Despite being one of our closest stellar neighbors, uncertainties remain in our understanding of its trajectory through space. One major factor contributing to these uncertainties is the star's proper motion, which is the apparent movement of the star across the sky as seen from Earth. While we can measure this motion with great precision using current telescopes, even tiny errors in these measurements can lead to significant discrepancies when projected over long periods. Another source of uncertainty lies in our knowledge of the star's radial velocity, which is its motion directly towards or away from Earth. This measurement is crucial for determining the star's true three-dimensional motion through space. However, slight inaccuracies in radial velocity measurements can also result in substantial differences in long-term predictions of the star's path. The gravitational influence of other celestial bodies adds another layer of complexity to these predictions. As Barnard's star travels through the galaxy, its path may be subtly altered by the gravitational pull of nearby stars, planets, or even dark matter. These effects are difficult to account for precisely, especially over extended timeframes, further complicating our ability to forecast the star's exact future position with complete certainty. Barnard's star, one of our closest stellar neighbors, is unlikely to have any significant effect on the orbits of our outer planets. Despite its proximity to our solar system, it is still incredibly far away in astronomical terms. The star is currently about 6 light-years from Earth, which is equivalent to about 57 trillion kilometers. At this distance, the gravitational influence of Barnard's star on our solar system is negligible. Our outer planets, such as Neptune and Uranus, are held firmly in their orbits by the Sun's much stronger gravitational pull. The Sun's mass is vastly greater than that of Barnard's star, which is a small red dwarf star with only about 16% of the Sun's mass. However, over extremely long timescales, measured in millions of years, Barnard's star is moving relative to our solar system. It is actually approaching us and will make its closest approach in about 10,000 years. Even at its closest, it will still be too far away to disrupt the orbits of our planets. While Barnard's star doesn't pose a threat to our planetary orbits, studying such nearby stars helps astronomers understand stellar movements and potential long-term influences on our cosmic neighborhood. This knowledge contributes to our broader understanding of galactic dynamics and the long-term stability of planetary systems. Barnard's star, despite being one of our closest stellar neighbors, is too far away to have any significant gravitational influence on the Kuiper belt. Located approximately 6 light-years from our solar system, Barnard's star is a small, dim red dwarf with relatively low mass. Its gravitational reach simply doesn't extend far enough to affect the objects in the outer regions of our solar system. The Kuiper belt, a region of icy bodies beyond Neptune's orbit, is primarily influenced by the gravity of our Sun and the giant planets within our solar system. These local gravitational forces are far more dominant in shaping the Kuiper belt's structure and the orbits of its objects. Even closer stars, like Alpha Centauri, which is only about 4 light-years away, have negligible gravitational effects on our solar system's outer regions. The vast distances between stars in our galaxy ensure that each star system remains largely isolated in terms of direct gravitational interactions. While Barnard's star doesn't disturb the Kuiper belt, it's worth noting that other factors, such as passing stars or the galactic tide, can have long-term effects on the outermost regions of our solar system, like the hypothetical Oort cloud. However, these influences occur over extremely long timescales and are not significant for the Kuiper belt. Barnard's star, the 4th closest star system to our Sun, could have significant effects on cometary orbits due to its proximity and motion through space. As one of our nearest stellar neighbors, located just 6 light-years away, its gravitational influence extends into the outer reaches of our solar system. The star's rapid proper motion across the sky, the fastest of any known star, means it is moving through space at high velocity relative to our Sun. This swift movement could potentially disrupt the orbits of long-period comets in the Oort cloud, the vast sphere of icy bodies surrounding our solar system. As Barnard's star passes through the outskirts of our solar system, its gravity might alter the trajectories of these distant comets. Some could be nudged closer to the inner solar system, potentially leading to an increase in cometary activity visible from Earth. Conversely, other comets might be deflected away, changing their orbits so they never approach the Sun. The effects of Barnard's star on cometary orbits would occur over extremely long timescales, likely millions of years. While not an immediate concern for Earth, these gravitational interactions highlight the dynamic nature of our cosmic neighborhood and the long-term influences distant stars can have on our solar system. Barnard's star, our celestial neighbor, is steadily moving closer to our solar system. This red dwarf star, located about 6 light-years away, is approaching us at a speed of approximately 140 kilometers per second. Despite this rapid approach, its influence on solar radiation reaching Earth will be minimal for the foreseeable future. The primary reason for this negligible impact is the vast distance between Barnard's star and our planet. Even at its closest approach, which will occur in about 10,000 years, it will still be more than 3.5 light-years away from us. This distance is far too great for Barnard's star to significantly affect the amount of solar radiation Earth receives. Our Sun, being much closer and far more luminous, will continue to be the dominant source of radiation for Earth. Barnard's star, despite its movement towards us, is a dim red dwarf with a luminosity less than 1,000th that of our Sun. Its contribution to the total radiation reaching Earth will remain imperceptible to us. While Barnard's star's approach won't noticeably change our solar radiation, it does offer astronomers a unique opportunity to study stellar movement and the dynamics of our local cosmic neighborhood. This celestial dance reminds us of the constant motion and evolution occurring in our universe, even if its effects on our daily lives remain unseen. Barnard's star, one of our closest stellar neighbors, lies about 6 light-years from Earth. While it's relatively near in cosmic terms, this distance is still far too great for its magnetic field to have any direct interaction with our Sun's magnetic field. Stellar magnetic fields, including those of Barnard's star and our Sun, typically extend into space around each star, forming what we call the stellar wind. For our Sun, this region is known as the heliosphere, which extends well beyond the orbit of Pluto. However, even this vast bubble of solar influence doesn't come close to reaching other stars. The space between stars, known as the interstellar medium, acts as a buffer zone. This region contains very tenuous gas and dust, along with cosmic rays and magnetic fields from the galaxy itself. These interstellar elements effectively separate the magnetic environments of individual stars. While Barnard's star and our Sun can't directly interact magnetically, both stars do contribute to and are influenced by the larger galactic magnetic field. This complex network of magnetic forces spans our entire Milky Way galaxy, shaping cosmic ray paths and influencing the formation of new stars on a grand scale. The exchange of matter between our solar system and Barnard's star is a fascinating concept that pushes the boundaries of our understanding of interstellar interactions. Barnard's star, located approximately 6 light-years away, is one of our closest stellar neighbors, making it an intriguing subject for studying potential matter exchange. The primary mechanism for such exchange would be through the ejection and capture of small bodies like comets, asteroids, or even planetary debris. These objects can be influenced by gravitational interactions with planets or passing stars, potentially altering their orbits dramatically. In some cases, these perturbations could be strong enough to eject objects from one star system and send them hurtling through interstellar space. However, the vast distances between star systems make such exchanges extremely rare. The space between stars is incredibly empty, and the chances of an ejected object from one system being captured by another are exceedingly low. Even over millions of years, the probability of significant matter exchange remains small. Despite these challenges, scientists have identified some intriguing possibilities. The discovery of interstellar objects like Oumuamua and comet Borisov passing through our solar system suggests that matter can indeed travel between star systems. While these particular objects were not from Barnard's star, they demonstrate that interstellar matter exchange does occur, opening up the possibility for similar interactions with our nearby neighbor. Barnard's star, our closest stellar neighbor after the Alpha Centauri system, is slowly making its way toward our solar system. This red dwarf star, located about 6 light-years away, is moving at a rapid pace of 140 kilometers per second relative to the Sun. Despite this swift approach, its effects on our solar system's space weather will be minimal for the foreseeable future. As Barnard's star draws nearer over the next several thousand years, its magnetic field may begin to interact with the heliosphere, the bubble of charged particles surrounding our solar system. This interaction could potentially cause subtle changes in the flow of cosmic rays and interstellar particles entering our region of space. However, these effects would be extremely small and likely undetectable without highly sensitive instruments. The star's approach might also lead to a slight increase in the density of interstellar material in our solar system's outer reaches. This could result in minor variations in the shape and size of the heliosphere, potentially altering the way our Sun's magnetic field interacts with the interstellar medium. Yet, these changes would occur gradually over millennia and would not significantly impact life on Earth or our planet's magnetic field. It's important to note that even at its closest approach, estimated to occur in about 10,000 years, Barnard's star will still be nearly 4 light-years away from our Sun. This vast distance ensures that any direct effects on our solar system's space weather will remain minimal, preserving the delicate balance that allows life to thrive on our planet. Barnard's star, the 4th closest star system to our Sun, is indeed an intriguing celestial neighbor. While it might seem plausible for its gravity to influence objects in our solar system, the reality is quite different. The vast distance between Barnard's star and our solar system makes any gravitational interaction extremely unlikely. Even at its closest approach, which will occur in about 10,000 years, Barnard's star will still be nearly 4 light-years away from us. This immense separation means that its gravitational influence on our solar system is negligible. Moreover, Barnard's star is a red dwarf, significantly smaller and less massive than our Sun. Its reduced mass further diminishes its gravitational reach, making it even less likely to affect objects within our solar system. However, it is worth noting that over extremely long timescales, measured in millions or billions of years, complex gravitational interactions between stars can potentially influence the paths of distant comets or other small objects in the outer reaches of star systems. But for all practical purposes, we can rest assured that Barnard's star poses no risk of capturing any significant objects from our cosmic neighborhood. As Barnard's star continues its journey through space, its eventual closest approach to our solar system will bring subtle yet fascinating changes to our night sky. This red dwarf star, currently the 4th closest star system to Earth, is steadily moving towards us and will make its nearest pass in approximately 10,000 years. During this closest approach, Barnard's star will become noticeably brighter in our sky. While it's currently too faint to be seen with the naked eye, it will likely become visible without the aid of telescopes, appearing as a dim, reddish point of light. This increased brightness won't rival that of our brightest stars, but it will add a new element to familiar constellations. The star's proper motion, or its apparent movement across the sky, will also become more pronounced. Keen observers might notice its position shifting relative to other stars over shorter periods, perhaps even within a human lifetime. This movement will offer a rare, visible demonstration of the dynamic nature of our galactic neighborhood. Interestingly, the close passage of Barnard's star might also affect how we see other stars. Its gravitational influence, though slight, could potentially alter the paths of comets in the outer reaches of our solar system, possibly directing some towards the inner planets. This could lead to an increase in comet sightings, adding occasional new streaks of light to our night sky. Barnard's star, the fourth closest star system to our own, is steadily approaching the solar system. This red dwarf star is moving towards us at a rapid pace of about 140 kilometers per second, faster than any other known star. Despite this swift approach, Barnard's star is still incredibly far away, currently at a distance of about 6 light years. The approach of Barnard's star could have significant implications for future space exploration plans. As it draws nearer over the coming millennia, it may become an increasingly attractive target for interstellar missions. The decreasing distance could make the journey more feasible with future propulsion technologies, potentially allowing us to study a different star system up close. However, it is important to note that the effects of this approach will unfold over an extremely long timescale. Even at its current speed, Barnard's star will take about 10,000 years to halve its distance to Earth. This means that any immediate impact on our space exploration plans will be minimal. Instead, the approach of Barnard's star serves as a long-term consideration for our descendants and future generations of astronomers and space explorers. The movement of Barnard's star also highlights the dynamic nature of our cosmic neighborhood. It reminds us that the positions of stars are not fixed, and that our plans for space exploration must take into account the changing landscape of our galactic environment over vast periods of time. Barnard's star is a fascinating target for amateur astronomers, offering a unique opportunity to observe one of our closest stellar neighbors. Located in the constellation Ophiuchus, this red dwarf star is just 6 light-years away from Earth, making it the fourth nearest star system to our own. To observe Barnard's star, amateur astronomers will need a telescope with at least a 6-inch aperture, as the star is too faint to be seen with the naked eye. Its visual magnitude of 9.5 means it's within reach of modest amateur equipment. The best time to look for Barnard's star is during the summer months in the northern hemisphere, when Ophiuchus is high in the night sky. One of the most intriguing aspects of observing Barnard's star is its rapid proper motion across the sky. It moves about 10 arc-seconds per year, which is faster than any other known star. This movement can be detected by taking photographs of the star field over several months or years and comparing the images. Patient observers can actually witness the star's journey through space, a rare and exciting experience in amateur astronomy. While Barnard's star may not be visually spectacular, its proximity and unique characteristics make it a rewarding target for amateur astronomers. Observing this ancient, dim star offers a tangible connection to the vast and dynamic nature of our galactic neighborhood. To view Barnard's star from Earth, amateur astronomers need a telescope with moderate power and a dark sky location. This red dwarf star, despite being one of the closest stars to our solar system at just 6 light-years away, is not visible to the naked eye due to its faint magnitude. A small telescope with an aperture of about 4 to 6 inches is typically sufficient to spot Barnard's star. However, larger telescopes will provide a clearer view. Because of its low brightness, observers should choose a night with good seeing conditions and minimal light pollution. Star charts or computerized telescope mounts can help locate Barnard's star in the constellation Ophiuchus. Its high proper motion, the fastest of any known star, means its position changes noticeably over the years, making it an interesting target for long-term observation. For astrophotographers, long-exposure images can capture this elusive star, revealing its distinctive red hue. Patience and persistence are key when observing Barnard's star, as its subtle appearance requires careful attention to detect against the backdrop of brighter celestial objects. Barnard's star, one of our closest stellar neighbors, has undergone subtle changes in visibility over the years. This red dwarf, located just 6 light-years away from Earth, has been a subject of fascination for astronomers since its discovery in 1916 by Edward Emerson Barnard. The star's visibility has been affected by its rapid proper motion across the night sky. Barnard's star moves at an astonishing rate of 10.3 arcseconds per year, which is the fastest proper motion of any known star. This movement has caused it to gradually shift position relative to other stars, altering its location in the night sky over time. Despite its proximity to Earth, Barnard's star remains invisible to the naked eye due to its low luminosity. Its apparent magnitude of approximately 9.5 has remained relatively constant. However, its position shift has made it more or less challenging to locate depending on its proximity to other celestial objects at different points in time. Interestingly, Barnard's star is approaching our solar system and will make its closest approach in approximately 11,000 years. At that time, it will come within about 3.8 light-years of Earth, potentially becoming slightly brighter in our night sky. This long-term change in distance will subtly affect its visibility, albeit on a timescale far beyond human lifespans. Barnard's star, one of the closest stars to our solar system, can be observed throughout most of the year from the northern hemisphere. However, the optimal time for viewing this elusive celestial object is during the summer months, particularly from June to September. During this period, the star reaches its highest point in the night sky, making it more easily visible to observers. Located in the constellation Ophiuchus, Barnard's star is best seen when Ophiuchus is high above the horizon. In the northern hemisphere, this occurs during the late evening hours of summer. As autumn approaches, the star becomes visible earlier in the night, but its position gradually shifts towards the western horizon. Despite its proximity to Earth, Barnard's star is challenging to spot with the naked eye due to its low luminosity. With a magnitude of approximately 9.5, it requires at least a small telescope or powerful binoculars to observe. Patient stargazers using these tools will be rewarded with a glimpse of this ancient red dwarf, which is moving across the sky faster than any other known star. For those in the southern hemisphere, observing Barnard's star can be more difficult, as it never rises very high above the northern horizon. However, it can still be seen during winter months, when Ophiuchus is visible in the night sky. Light pollution significantly hampers our ability to observe Barnard's star, despite it being one of the closest stars to our solar system. This red dwarf star, located just 6 light-years away, is naturally dim and challenging to spot even under ideal conditions. The increasing glow of artificial lights from urban areas creates a veil of brightness in the night sky, effectively drowning out the faint light from distant celestial objects. In areas with severe light pollution, the sky background becomes so bright that it overwhelms the light from Barnard's star, making it virtually impossible to see with the naked eye or even small telescopes. This problem extends beyond just Barnard's star, affecting our view of countless other stars, nebulae, and galaxies. Amateur astronomers and stargazers often need to travel to remote, dark sky locations to escape the effects of light pollution and observe faint objects like Barnard's star. Even professional observatories are increasingly affected by this issue, with many being relocated to higher altitudes or more isolated areas to preserve their ability to conduct sensitive astronomical observations. The impact of light pollution on our ability to see Barnard's star serves as a reminder of how human activities can inadvertently limit our connection to the cosmos. It underscores the importance of dark sky preservation efforts and the need for more efficient, directed lighting in urban areas to minimize interference with astronomical observations. Professional astronomers employ a variety of advanced techniques to study Barnard's star, one of our closest stellar neighbors. High-precision astrometry is a key method, allowing scientists to measure the star's position and movement with exceptional accuracy. This technique has revealed Barnard's star's rapid proper motion across the sky, the fastest of any known star. Spectroscopy plays a crucial role in analyzing the star's composition and temperature. By examining the light emitted by Barnard's star, astronomers can determine its chemical makeup and classify it as a red dwarf. This method also helps in measuring the star's radial velocity, which is essential for detecting potential orbiting planets. Another important technique is photometry, which involves measuring the star's brightness over time. This can reveal subtle variations that might indicate the presence of star spots or flares, providing insights into the star's activity levels. Additionally, adaptive optics and interferometry allow astronomers to obtain sharper, more detailed images of Barnard's star, potentially resolving features on or near its surface. Lastly, long-term monitoring programs track Barnard's star over extended periods, searching for signs of orbiting planets through methods such as the radial velocity technique and astrometric measurements. These ongoing observations have led to the tentative detection of a super-Earth-sized exoplanet, showcasing the power of persistent and precise astronomical study. Space-based telescopes have revolutionized our observations of Barnard's star, offering unprecedented clarity and precision. These advanced instruments, orbiting high above Earth's atmosphere, eliminate the distortions and limitations that ground-based telescopes face. The Hubble Space Telescope, for instance, has provided sharp images of Barnard's star, allowing astronomers to study its characteristics in great detail. This has been crucial in measuring the star's proper motion, which is the highest of any known star relative to our solar system. Space telescopes have also enabled more accurate measurements of Barnard's star's parallax, helping refine our understanding of its distance from Earth. Moreover, these orbital observatories have been instrumental in the search for exoplanets around Barnard's star. The exquisite sensitivity of space-based instruments has allowed scientists to detect minute wobbles in the star's position, potentially indicating the presence of orbiting planets. This capability has led to the discovery of a candidate planet, Barnard's star B, although its existence is still debated. Space telescopes also offer the advantage of continuous observation, unhampered by day-night cycles or weather conditions. This has allowed for long-term monitoring of Barnard's star, providing valuable data on its behavior over time, including any variations in brightness or spectral characteristics that might indicate stellar activity or long-term changes. Imaging Barnard's star presents several unique challenges for astronomers. Despite being one of our closest stellar neighbors at just 6 light-years away, this red dwarf star is exceptionally faint. Its dim nature makes it difficult to capture clear, detailed images even with advanced telescopes. The star's high proper motion, the fastest of any known star, adds another layer of complexity. Barnard's star moves across our sky at a rapid pace, changing its position noticeably over relatively short periods. This movement requires astronomers to constantly update their calculations and adjust their equipment to track the star accurately. Furthermore, the search for potential planets orbiting Barnard's star is particularly demanding. Any planets in its system would be small and incredibly close to the star, making them nearly impossible to detect through direct imaging. Instead, astronomers must rely on indirect methods such as radial velocity measurements, which look for tiny wobbles in the star's motion caused by orbiting planets. Lastly, the star's age and low metallicity make it an intriguing but challenging subject for study. Understanding its composition and evolution requires highly sensitive spectroscopic observations, pushing the limits of our current technology. Despite these obstacles, the potential insights into stellar evolution and planetary formation continue to drive efforts to better image and study Barnard's star. Adaptive optics technology has revolutionized our ability to observe Barnard's star with unprecedented clarity and precision. This advanced system compensates for the distortions caused by Earth's turbulent atmosphere, allowing ground-based telescopes to capture images nearly as sharp as those taken from space. For Barnard's star, one of our closest stellar neighbors at just 6 light-years away, adaptive optics has enabled astronomers to study its characteristics in remarkable detail. We can now better measure its size, temperature, and even detect subtle variations in its brightness that might indicate the presence of orbiting planets. The technology has also improved our ability to track Barnard's star's rapid proper motion across the night sky. As the fastest moving star visible to the naked eye, it shifts its position noticeably over human timescales. Adaptive optics allows us to measure this motion with extreme accuracy, refining our understanding of stellar dynamics and galactic structure. Furthermore, adaptive optics has enhanced our capacity to search for potential exoplanets around Barnard's star. By providing clearer images and more precise measurements, it increases our chances of detecting the tiny wobbles or dips in brightness that could signal the presence of orbiting worlds. This has contributed to the ongoing quest to understand the prevalence and nature of planetary systems around red dwarf stars like Barnard's star. Several future missions are set to enhance our understanding of Barnard's star and its potential planetary system. The European Space Agency's Gaia mission, already in operation, will continue to provide precise measurements of the star's position and motion, refining our knowledge of its properties and any orbital variations that might indicate the presence of planets. NASA's James Webb Space Telescope, the most powerful space observatory ever built, will be capable of studying Barnard's star in unprecedented detail. Its advanced instruments could potentially characterize the atmosphere of any confirmed planets orbiting the star, offering insights into their composition and potential habitability. Ground-based observatories are also joining the effort. The extremely large telescope, currently under construction in Chile, will have the power to directly image large planets around nearby stars, potentially including any that might orbit Barnard's star. This could provide visual confirmation of the planet candidate discovered in 2018. Additionally, ongoing radial velocity surveys using high-precision spectrographs on various telescopes worldwide will continue to monitor Barnard's star, looking for subtle shifts in its spectrum that could reveal the gravitational influence of orbiting planets. These combined efforts promise to significantly advance our understanding of this intriguing stellar neighbor in the coming years. Barnard's star has captured the imagination of science fiction authors for decades, appearing in numerous stories and novels. This nearby red dwarf, located just 6 light-years from Earth, has been a popular setting for tales of interstellar exploration and alien encounters. In many works, Barnard's star serves as an early destination for human space travelers, often portrayed as one of the first stars humans visit beyond our solar system. Some stories depict it as home to alien civilizations, while others use it as a waypoint for further cosmic adventures. One notable appearance of Barnard's star is in Robert Forward's novel Rocheworld, where a human expedition discovers a unique double-planet system orbiting the star. Other authors have used the star's real-world characteristics, such as its high proper motion across the sky, as plot elements in their stories. The enduring fascination with Barnard's star in science fiction reflects both its proximity to Earth and the ongoing scientific interest in searching for exoplanets around this nearby stellar neighbor. As our understanding of the star evolves, it continues to inspire new stories that blend scientific fact with imaginative speculation. Barnard's star has captured the imagination of science fiction writers and filmmakers due to its proximity to our solar system and its potential for harboring exoplanets. In the realm of television, this nearby red dwarf star played a significant role in the classic British science fiction series Blake's 7. The show's creators used Barnard's star as a key location in their fictional universe, highlighting its importance in space exploration narratives. Moving to the silver screen, Barnard's star featured prominently in the thought-provoking film Voyage to the Prehistoric Planet. This science fiction adventure, released in the 1960s, used the star as a destination for its interplanetary explorers, showcasing the fascination with nearby stellar objects during the early days of space exploration. More recently, Barnard's star has been mentioned in various documentaries about space and exoplanet discovery. These non-fiction productions often use the star as an example when discussing the search for habitable worlds beyond our solar system, emphasizing its relevance in both scientific research and popular culture. While not as frequently featured as some other celestial objects, Barnard's star continues to intrigue creators and audiences alike, serving as a tangible connection between our current scientific understanding and the boundless possibilities of space exploration in fiction. Barnard's star has played a significant role in shaping space exploration narratives, capturing the imagination of scientists and the public alike. As the fourth closest star system to our Sun, located just 6 light-years away, it has long been viewed as a potential target for future interstellar missions. The star's rapid proper motion across the night sky, the fastest of any known star, has made it a subject of intense study. This movement, first noted by astronomer Edward Emerson Barnard in 1916, has allowed scientists to accurately measure its distance and properties, making it one of the most well-characterized stars beyond our solar system. In the mid-20th century, claims of planets orbiting Barnard's star sparked excitement about the possibility of nearby alien worlds. Although these initial planet detections were later disproven, they fueled scientific and popular interest in exoplanet searches. This enthusiasm contributed to the development of more advanced planet-hunting techniques and missions. More recently, the discovery of a super-Earth orbiting Barnard's star has reignited interest in this nearby stellar neighbor. This finding has not only expanded our understanding of planetary formation around red dwarf stars, but has also reinforced the idea that potentially habitable worlds might exist in our cosmic backyard, inspiring continued efforts in both exoplanet research and the conceptualization of future interstellar exploration. Barnard's star has been a subject of fascination in both scientific circles and popular media, but several misconceptions have taken root over the years. One common misunderstanding is that Barnard's star definitely has planets orbiting it. While it was long suspected to host planetary companions, early claims of planet detections around Barnard's star were later debunked. It was not until 2018 that a planet was confirmed orbiting this nearby red dwarf. Another prevalent misconception is that Barnard's star is rapidly approaching our solar system and will soon become the closest star to Earth. While it is true that Barnard's star has the highest proper motion of any known star, meaning it appears to move quickly across our sky, it is not on a collision course with our solar system. In fact, it will make its closest approach in approximately 10,000 years, and even then, it will remain about 3.5 light-years away from us. Some popular accounts have also exaggerated the potential for Barnard's star to host life. Given its age and low luminosity, any planets orbiting this star would likely be cold and inhospitable. The confirmed planet, Barnard's star B, is thought to be a super-Earth orbiting near the star's snowline, making it too cold for liquid water on its surface under most circumstances. Lastly, there is a misconception that Barnard's star is a typical red dwarf. In reality, it is an unusually old and metal-poor star, making it quite different from many other red dwarfs in our galactic neighborhood. These unique characteristics make Barnard's star an intriguing subject for scientific study, beyond its status as one of our closest stellar neighbors. Barnard's star has captured the imagination of artists in various forms of media, particularly in science fiction and space art. This small, dim red dwarf star, located just 6 light-years from Earth, has been a popular subject due to its proximity and the possibility of hosting exoplanets. In visual arts, painters and digital artists have often depicted Barnard's star as a reddish orb dominating alien landscapes. These artworks frequently showcase hypothetical planets orbiting the star, with imaginative terrains and atmospheres reflecting the red light of their parent star. Some artists have explored the concept of interstellar travel, portraying futuristic spacecraft approaching or orbiting Barnard's star. Science fiction literature has also embraced Barnard's star as a setting for numerous stories and novels. Authors have speculated about potential civilizations, alien ecosystems, and human colonies existing in the star system. The star's real-world characteristics, such as its high proper motion across the sky, have been incorporated into these narratives, adding a layer of scientific authenticity to the fictional tales. In film and television, Barnard's star has been referenced in various science fiction productions, often as a destination for interstellar missions or as the origin of alien visitors to Earth. These artistic interpretations not only entertain, but also serve to spark public interest in astronomy and the search for exoplanets, highlighting the fascinating nature of our stellar neighborhood. Barnard's star has been a focal point in discussions about extraterrestrial life due to its proximity to our solar system. As the fourth closest star to the Sun, located just 6 light-years away, it has long captured the imagination of scientists and the public alike. In the 1960s, astronomer Peter van der Kamp claimed to have detected planets orbiting Barnard's star. This announcement sparked excitement about the possibility of habitable worlds in our cosmic neighborhood. However, subsequent observations failed to confirm these planets, and it was later determined that the supposed detections were likely due to instrumental errors. Despite this setback, Barnard's star remained a prime target for exoplanet searches. Its status as a red dwarf star, the most common type of star in our galaxy, made it an intriguing candidate for hosting potentially habitable worlds. Red dwarfs are smaller and cooler than our Sun, allowing planets to orbit much closer while still maintaining temperatures suitable for liquid water. In 2018, astronomers announced the discovery of a super-Earth orbiting Barnard's star. While this planet is likely too cold to support life as we know it, its existence reignited interest in the star system. The discovery demonstrated that planet formation can occur around even the oldest stars in our galaxy, as Barnard's star is estimated to be twice as old as our Sun. This finding has broadened our understanding of where we might find extraterrestrial life, encouraging scientists to look not just at young, Sun-like stars, but also at the numerous red dwarfs that populate our galactic neighborhood. Barnard's star has played a significant role in astronomy education, serving as a prime example of stellar motion and the dynamic nature of our cosmic neighborhood. As one of the closest stars to our solar system, located just 6 light-years away, it offers students a tangible connection to the vast universe beyond our planet. Educators often use Barnard's star to demonstrate proper motion, the apparent movement of a star across the sky as seen from Earth. This red dwarf exhibits the fastest proper motion of any known star, moving at a rate that allows its movement to be detected over human timescales. This makes it an excellent tool for teaching students about the constant motion of celestial objects and how astronomers measure distances in space. Barnard's star also features prominently in discussions about exoplanet detection methods. For decades, astronomers searched for planets orbiting this nearby star, using it to explain techniques such as the radial velocity method and astrometry. Although initial claims of planets were later disproven, these false positives served as valuable lessons in the challenges of exoplanet detection and the importance of rigorous scientific verification. Furthermore, Barnard's star helps illustrate the diversity of stellar types in our galaxy. As a small, cool red dwarf, it contrasts sharply with our Sun, allowing educators to explore the range of star sizes, temperatures, and lifespans. This comparison helps students grasp the complex nature of stellar evolution and the variety of environments that might exist around different types of stars in our universe. Barnard's star has earned several nicknames over the years, reflecting its unique characteristics and importance in astronomical studies. Astronomers often refer to it as the runaway star due to its exceptionally high proper motion across the night sky. This rapid movement makes it appear to be fleeing from Earth, though in reality, it's simply a close neighbor moving quickly through space. Another common moniker for Barnard's star is the Greyhound of the skies, again referencing its swift apparent motion. This name paints a vivid picture of the star racing across the celestial sphere, much like the speedy dog breed. Some scientists have also dubbed it the flying star, emphasizing its perceived rapid movement from our earthly vantage point. Given its proximity to our solar system, Barnard's star is sometimes called our friendly neighbor or the second nearest star, acknowledging its position as the next closest star system after the Alpha Centauri triple star system. These names highlight the star's significance in our cosmic neighborhood and its role in helping astronomers understand nearby stellar environments. Lastly, some researchers informally refer to Barnard's star as the benchmark star. This nickname stems from its frequent use as a reference point in various astronomical studies, particularly those focusing on low-mass stars and the search for exoplanets around red dwarfs. Its well-studied nature and proximity make it an excellent standard for comparing other similar stars and systems. Social media has significantly amplified public awareness of Barnard's star, bringing this celestial neighbor into the spotlight for astronomy enthusiasts and casual stargazers alike. As the fourth closest star system to our Sun, Barnard's star has long fascinated astronomers, but social media platforms have expanded its reach to a broader audience. Astronomical organizations and space agencies now regularly share updates, images, and discoveries related to Barnard's star on platforms such as Twitter, Facebook, and Instagram. These posts often include stunning visualizations and easy-to-understand explanations, making complex astronomical concepts more accessible to the general public. The discovery of a potential exoplanet orbiting Barnard's star in 2018 sparked a flurry of social media activity. News of this super-Earth candidate spread rapidly across various platforms, igniting discussions and sparking curiosity about our stellar neighborhood. This event demonstrated how social media can quickly disseminate scientific discoveries, fostering public engagement with astronomy. Moreover, citizen science projects focused on Barnard's star have gained traction through social media promotion. These initiatives allow amateur astronomers to contribute to ongoing research, creating a sense of community and shared scientific exploration. As a result, Barnard's star has become not just a subject of professional study, but a point of connection for space enthusiasts worldwide, showcasing the power of social media in bridging the gap between scientific research and public interest in astronomy. Barnard's star, one of our closest stellar neighbors, has captured the imagination of various cultures and societies since its discovery in 1916. In scientific circles, it holds a special place as a benchmark for studying stellar motion and the search for exoplanets. Astronomers have long used it as a prime target for planet-hunting missions, making it a symbol of our quest to find other worlds beyond our solar system. In popular culture, particularly in science fiction literature and media, Barnard's star has become a frequent setting for interstellar adventures. Its proximity to Earth makes it an attractive destination for fictional space travelers, often serving as a first stop on longer journeys or as a home for alien civilizations. This has cemented its place in the collective imagination as a tangible connection to the wider universe. For amateur astronomers, Barnard's star represents an achievable observing challenge. Its visibility through modest telescopes, combined with its rapid, proper motion across the sky, makes it a favorite target for stargazers. This accessibility has turned the star into a symbol of the wonders of the night sky that are within reach of everyday enthusiasts. In some futurist and space exploration circles, Barnard's star is seen as a potential early target for interstellar missions. Its relative closeness makes it one of the most realistic destinations for proposed long-term space travel projects, embodying humanity's aspirations to reach beyond our solar system and explore the stars firsthand. Barnard's star, one of our closest stellar neighbors at just 6 light-years away, has long fascinated astronomers. In 2018, scientists announced the discovery of a candidate exoplanet orbiting this red dwarf star. This potential world, dubbed Barnard's star B, is believed to be a super-Earth, with a mass roughly 3 times that of our home planet. The planet's orbit takes it around Barnard's star once every 233 Earth days. This places it near the star's snowline, the distance at which volatile compounds like water can condense into solid ice. As a result, Barnard's star B is likely a frigid world, with surface temperatures estimated to be around -170 degrees Celsius. While the existence of Barnard star B is still considered tentative and requires further confirmation, its potential discovery marks a significant milestone in exoplanet research. The planet was detected using the radial velocity method, which measures tiny wobbles in the star's motion caused by the gravitational pull of an orbiting planet. The search for planets around Barnard star continues as astronomers use increasingly sensitive instruments to probe this nearby system. The star's proximity to Earth makes it an excellent target for future studies, potentially allowing us to learn more about the formation and evolution of planetary systems around low-mass stars. Astronomers have employed several sophisticated techniques to hunt for planets orbiting Barnard star. One primary method has been the radial velocity technique, which detects minute wobbles in the star's motion caused by the gravitational pull of orbiting planets. This approach has been particularly useful for Barnard star due to its proximity to Earth and its relatively low mass, making potential planetary influences more noticeable. Another crucial method has been high-precision astrometry, which measures the star's position in the sky with extreme accuracy. By tracking tiny changes in the star's position over time, scientists can infer the presence of unseen companions. The European Space Agency's Gaia mission has provided invaluable data for this purpose, allowing for unprecedented precision in stellar position measurements. Astronomers have also utilized the transit method, watching for periodic dips in the star's brightness that might indicate a planet passing in front of it. However, this technique has been less fruitful for Barnard star, as any planets would need to be aligned just right to be detected this way. Additionally, researchers have used direct imaging techniques, attempting to capture light from any planets themselves, though this remains challenging due to the extreme brightness difference between the star and potential planets. These diverse approaches have led to intriguing results, including the potential discovery of a super-Earth orbiting Barnard star. However, the search continues as confirming planetary candidates and potentially finding smaller, more Earth-like worlds requires ongoing observations and increasingly sensitive instruments. Barnard star presents unique challenges and opportunities in the search for exoplanets. As one of our closest stellar neighbors, located just 6 light-years away, it offers astronomers an excellent target for study. However, its nature as a red dwarf star complicates the search. Red dwarfs like Barnard star are much cooler and dimmer than our Sun, which means their habitable zones, where liquid water could exist on a planet's surface, are much closer to the star. This proximity makes it easier to detect planets using methods like the radial velocity technique, which measures tiny wobbles in the star's motion caused by orbiting planets. The search for exoplanets around Barnard star has been ongoing for decades, with several false alarms along the way. In 2018, astronomers announced the discovery of a super-Earth orbiting the star, although this finding remains controversial and requires further confirmation. The planet, if it exists, would be about 3 times the mass of Earth and orbit the star every 233 days. One of the most intriguing aspects of studying Barnard star is its high proper motion, meaning it appears to move rapidly across the sky relative to other stars. This movement allows astronomers to use a technique called astrometry, which measures the precise position of the star over time to detect the gravitational influence of any orbiting planets. As technology improves, this method may reveal smaller, more Earth-like worlds around this fascinating stellar neighbor. Detecting planets around red dwarf stars like Barnard star presents several unique challenges for astronomers. These small, cool stars, while numerous in our galaxy, pose difficulties that require specialized techniques and advanced technology to overcome. One major challenge is the faintness of red dwarf stars. Their dim nature makes it harder to gather enough light for precise measurements, especially when searching for the subtle signs of orbiting planets. This issue is compounded by the fact that any planets in the habitable zone of a red dwarf would orbit very close to the star, making them even more difficult to distinguish from the stellar glare. Red dwarfs are also known for their stellar activity, including frequent flares and star spots. These phenomena can create false signals that mimic the presence of a planet, leading to potential misidentifications. Astronomers must carefully analyze data over long periods to separate true planetary signals from stellar noise. The proximity of potential planets to their host red dwarf also means they likely experience tidal locking, with one side perpetually facing the star. This complicates our understanding of their potential habitability and makes it challenging to interpret any atmospheric signatures we might detect. Despite these hurdles, the study of red dwarf systems remains crucial, as these stars and their planets are among the most common in our cosmic neighborhood. The discovery of Barnard's star B has significantly expanded our knowledge of planetary formation and diversity in the cosmos. This exoplanet, orbiting Barnard's star, one of our closest stellar neighbors, has forced astronomers to reconsider some of their theories about how planets form and where they can exist. Barnard's star B is what we call a super-Earth, a planet larger than our own but smaller than the ice giants like Neptune. Its discovery in a relatively cold orbit around a red dwarf star challenges previous assumptions about planet formation in such environments. Scientists had long thought that red dwarfs, being smaller and cooler than our Sun, might not have enough material in their protoplanetary disks to form larger planets. This finding suggests that planet formation processes might be more robust and adaptable than previously believed. It indicates that even in less than ideal conditions, with less material available and lower temperatures, substantial planets can still form. This has led to a re-evaluation of the potential for planet formation around other red dwarf stars, which are the most common type of star in our galaxy. Furthermore, the existence of Barnard's star B in what's known as the snow line, where volatile compounds like water can condense into solid ice, provides valuable insights into how planets might accumulate mass in these regions. This could help explain the formation of both rocky planets and the cores of gas giants, potentially bridging our understanding of these two types of planetary bodies. The discovery of a super-Earth orbiting Barnard's star is a significant milestone in our quest to understand planetary systems beyond our own. Barnard's star, located just 6 light-years away, is the second closest star system to our Sun, making it an object of great interest to astronomers and space enthusiasts alike. This super-Earth, estimated to be about 3 times the mass of our planet, orbits Barnard's star at a distance similar to that between Mercury and the Sun. Its proximity to Earth makes it an ideal candidate for future studies, potentially allowing us to learn more about the formation and evolution of planets around low-mass stars. The significance of this discovery extends beyond the realm of astronomy. It provides valuable insights into the prevalence of planets in our galactic neighborhood and suggests that rocky planets might be common around nearby stars. This finding bolsters our understanding of planetary formation processes and increases the likelihood of finding potentially habitable worlds in our cosmic backyard. Furthermore, the detection of this super-Earth showcases the remarkable advancements in our planet-hunting technologies. It demonstrates our growing ability to detect smaller, rocky planets around distant stars, bringing us closer to answering one of humanity's most profound questions: are we alone in the universe? Barnard's star, a small red dwarf located just 6 light-years from Earth, has long intrigued astronomers due to its proximity and potential for hosting habitable worlds. However, when comparing the habitability of planets around Barnard's star to other systems, several factors come into play that make it less promising than some of its stellar neighbors. The most significant challenge for potential life around Barnard's star is its low luminosity. As a red dwarf, it emits far less energy than our Sun, meaning that its habitable zone, the region where liquid water could exist on a planet's surface, is much closer to the star. This proximity poses risks, as planets in this zone would likely be tidally locked, with one side perpetually facing the star. Such conditions could lead to extreme temperature differences between the day and night sides, potentially making it difficult for life as we know it to thrive. Furthermore, red dwarfs like Barnard's star are known for their stellar activity, including frequent flares and radiation bursts. These events could strip away the atmospheres of nearby planets over time, further reducing their habitability. In contrast, systems with larger, more stable stars often provide more favorable conditions for life to develop and persist. While a planet candidate has been detected around Barnard's star, it is thought to be a cold super-Earth, likely too frigid to support life as we know it. When compared to systems like TRAPPIST-1 or those around other nearby stars such as Proxima Centauri, the potential for habitability around Barnard's star appears less promising, though continued research may yet reveal surprising possibilities in this nearby cosmic neighborhood. Several space agencies and research institutions have their sights set on Barnard's star for future exoplanet studies. The European Space Agency is developing the Plato mission, set to launch in 2026. This space observatory will use an array of telescopes to detect and characterize exoplanets, including any that might orbit Barnard's star. NASA's James Webb Space Telescope, already in operation, has the capability to study the atmospheres of exoplanets. It could potentially observe any confirmed planets around Barnard's star, providing invaluable data about their composition and potential habitability. Ground-based observatories are also joining the search. The extremely large telescope, under construction in Chile, will have the power to directly image some exoplanets. Once operational in the mid-2020s, it could potentially capture images of any large planets orbiting Barnard's star. These missions, working in concert, will greatly enhance our understanding of Barnard's star and its potential planetary system. They represent the next wave of exoplanet research, promising to reveal new insights about these distant worlds and perhaps even signs of life beyond our solar system. The search for planets around Barnard's star has been a fascinating journey spanning several decades. Barnard's star, a red dwarf located just 6 light-years from Earth, has long captivated astronomers due to its proximity and potential for harboring worlds. In the 1960s, astronomer Peter van der Kamp claimed to have detected a gas giant orbiting Barnard's star. His announcement stirred excitement in the scientific community, as it would have been the first exoplanet discovery. However, subsequent studies in the 1970s and 80s failed to confirm van der Kamp's findings, and his claim was eventually dismissed as an error caused by equipment issues. The quest for planets around Barnard's star entered a new era with the advent of more advanced detection methods. High-precision radial velocity measurements and improved imaging techniques allowed astronomers to conduct more rigorous searches. These efforts finally bore fruit in 2018 when an international team of researchers announced the discovery of a super-Earth orbiting Barnard's star. This exoplanet, named Barnard's star B, is estimated to be about 3 times the mass of Earth and orbits its host star every 233 days. While the planet is likely too cold to support life as we know it, its discovery marked a significant milestone in the long history of planetary searches around this nearby star. The evolving search for planets around Barnard's star showcases the persistence of astronomers and the rapid advancements in exoplanet detection technology. The discovery of planets orbiting Barnard's star has significant implications for our understanding of planet distribution across the Milky Way galaxy. As one of our closest stellar neighbors, located just 6 light-years away, Barnard's star provides valuable insights into planetary formation and prevalence. The existence of planets around this low-mass red dwarf star suggests that planet formation is a common process, even for smaller, cooler stars. This finding supports the idea that planets may be more abundant throughout the galaxy than previously thought. It indicates that a diverse range of stellar environments can host planetary systems, not just those similar to our Sun. Furthermore, the types of planets found around Barnard's star, a super-Earth and potentially smaller rocky worlds, hint at the possibility of a higher frequency of terrestrial planets in the galaxy. This aligns with recent exoplanet surveys that have revealed an abundance of Earth-sized to super-Earth planets orbiting various types of stars. These discoveries challenge our previous assumptions about planet formation and distribution, prompting scientists to revise models of galactic planet populations. As we continue to study nearby stars like Barnard's star, we gain a clearer picture of the true diversity and ubiquity of planets in our galaxy, bringing us closer to understanding how common planetary systems and potentially habitable worlds might be across the vast expanse of the Milky Way. Barnard's star, a small red dwarf located just 6 light-years from Earth, has long fascinated astronomers and exoplanet hunters. While no confirmed planets orbit this nearby stellar neighbor, the possibility of life existing in its vicinity remains an intriguing question. The star's advanced age, estimated at around 10 billion years, suggests that any planets in its system would have had ample time to develop complex life forms. However, red dwarfs like Barnard's star pose unique challenges for potential habitable worlds. These stars are prone to intense flares and emit high levels of ultraviolet radiation, which could strip away planetary atmospheres and bombard surfaces with harmful radiation. Despite these obstacles, some scientists argue that life could potentially adapt to such harsh conditions. If a planet orbiting Barnard's star had a strong magnetic field and a thick atmosphere, it might shield its surface from the worst effects of stellar activity. Additionally, any life forms that evolved in this environment might develop unique adaptations to withstand the challenges posed by a red dwarf host star. The search for planets around Barnard's star continues, with astronomers using increasingly sensitive detection methods. While the existence of life-bearing worlds in this system remains speculative, the ongoing exploration of our stellar neighborhood brings us closer to understanding the potential for life beyond Earth. Barnard's star, a small red dwarf located just 6 light-years from Earth, presents unique challenges for potential habitability. Its diminutive size and cool temperature mean that any planets orbiting within its habitable zone would need to be much closer to the star than Earth is to our Sun. This proximity creates several issues for life as we know it. The intense gravitational pull exerted on these close-in planets would likely result in tidal locking, where one side of the planet always faces the star. This could lead to extreme temperature differences between the day and night sides, potentially making it difficult for life to thrive across the entire planet's surface. Red dwarfs like Barnard's star are also known for their volatile nature, often unleashing powerful flares that could strip away the atmospheres of nearby planets over time. These stellar outbursts would bombard any orbiting worlds with high-energy radiation, potentially sterilizing their surfaces and making it challenging for complex life to evolve. Despite these hurdles, the longevity of red dwarfs offers a potential advantage. With lifespans measured in trillions of years, these stars provide stable energy sources for much longer than larger stars like our Sun. This extended timeline could allow for the possibility of life emerging and evolving, given enough time and the right conditions. The search for habitable worlds around Barnard's star continues as astronomers seek to understand the complex interplay between red dwarfs and their planetary systems. Barnard's star, a dim red dwarf located just 6 light-years from Earth, presents a challenging environment for potential life. Any organism surviving in this system would need to adapt to extreme conditions. The star's low luminosity means that habitable planets would need to orbit very close, subjecting them to intense radiation and potential tidal locking. Hypothetical life forms in the Barnard star system might evolve to thrive in low-light conditions, perhaps developing highly efficient photosynthetic processes or relying on chemosynthesis instead. These organisms could have protective mechanisms against radiation, such as reflective outer layers or the ability to repair DNA damage quickly. If a planet in the system is tidally locked, organisms on the dark side might evolve to navigate using other senses, like echolocation or electromagnetic field detection. They could potentially derive energy from thermal vents or other geological processes. On the light side, life might develop extreme heat resistance and efficient water conservation methods. Given the harsh conditions, microbial life forms might be more likely to survive than complex multicellular organisms. However, if more complex life did evolve, it might possess unique features like bioluminescence to communicate in the dim light or multiple layers of protective tissue to shield against radiation. The key to survival in such an environment would be extreme adaptability and resilience. Barnard's star, a red dwarf located just 6 light-years from Earth, is one of our closest stellar neighbors. Its advanced age, estimated to be around 10 billion years old, significantly impacts the potential for life in its system. This venerable star has been shining for more than twice as long as our Sun, providing a vast timescale for potential biological evolution. The star's longevity offers an intriguing prospect for life to develop and flourish. Over billions of years, planets orbiting Barnard's star would have had ample time for complex chemistry to evolve into potential life forms. However, the star's age also presents challenges. As red dwarfs age, they tend to become more stable, with fewer violent flares and eruptions that could strip away planetary atmospheres or bombard surfaces with harmful radiation. Yet, the very qualities that make Barnard's star stable in its old age may have posed significant hurdles for life in its early years. Young red dwarfs are notoriously active, emitting powerful flares and stellar winds that could have stripped away the atmospheres of any planets orbiting too closely. This early volatile period might have sterilized potentially habitable worlds before life had a chance to gain a foothold. The age of Barnard's star also influences the types of planets we might expect to find in its system. Over billions of years, the star's gravitational influence could have altered planetary orbits, potentially ejecting some worlds while drawing others into more stable configurations. This long period of gravitational interaction might have created a more ordered system, potentially providing stable conditions conducive to life on any surviving planets. Barnard's star, a red dwarf located just 6 light-years from Earth, has been a subject of intense study for astronomers searching for potentially habitable worlds. The star's flare activity plays a crucial role in determining the possibility of life existing on any planets orbiting it. Red dwarfs like Barnard's star are known for their frequent and intense stellar flares. These explosive events release enormous amounts of energy and radiation, including harmful ultraviolet and X-rays. Such powerful outbursts can have devastating effects on nearby planets, potentially stripping away their atmospheres and bombarding their surfaces with dangerous radiation. However, recent observations have shown that Barnard's star is relatively quiet compared to other red dwarfs. Its flare activity is less frequent and less intense, which could be good news for any potential life forms in its system. This reduced stellar activity might allow planets to retain their atmospheres and develop the conditions necessary for life to emerge and thrive. Despite this relative calm, the close proximity of any habitable zone planets to Barnard's star still poses challenges. Even with reduced flare activity, the radiation exposure would likely be higher than what we experience on Earth. Any life forms that might exist would need to evolve robust protection mechanisms against this increased radiation, possibly developing in subsurface environments or under protective layers of ice or water. Barnard's star, located just 6 light-years from Earth, offers astronomers a unique opportunity for detailed observations of a nearby stellar system. Its close proximity allows for more precise measurements and potentially higher resolution imaging compared to more distant stars. This advantage could prove crucial in the search for habitable worlds and potential biosignatures. Future studies of Barnard's star's potential biosphere would benefit greatly from its nearness. Advanced telescopes and instruments could potentially detect smaller, rocky planets in the star's habitable zone with greater ease. The shorter distance also means that any light or radio signals from a potential civilization would be stronger and more detectable should they exist. However, Barnard's star presents some challenges. It is a red dwarf, much smaller and cooler than our Sun, which means its habitable zone is much closer to the star. Planets in this zone might be tidally locked, with one side always facing the star. This could create extreme temperature differences across the planet's surface, potentially affecting the development of life. Despite these challenges, the proximity of Barnard's star makes it an excellent target for future exoplanet missions and astrobiological studies. Its closeness allows for more frequent observations and potentially even direct imaging of any planets orbiting it, providing valuable data about planetary formation and the potential for life around red dwarf stars. Scientists searching for signs of life in Barnard's star's planetary system would focus on several key biosignatures. These indicators of potential biological activity are crucial in the hunt for extraterrestrial life. One primary biosignature would be the presence of oxygen in a planet's atmosphere. On Earth, oxygen is largely produced by photosynthetic organisms, so detecting significant amounts of oxygen could suggest the presence of life. However, scientists would need to rule out non-biological sources of oxygen before drawing any conclusions. Another important biosignature is methane. While methane can be produced through geological processes, its presence alongside oxygen could indicate biological activity. On Earth, methane is produced by various organisms, from bacteria to large animals. Water is also a critical component for life as we know it. Scientists would look for spectral signatures of water vapor in a planet's atmosphere or evidence of liquid water on its surface. Additionally, they might search for signs of vegetation by looking for the red edge, a sharp change in reflectance of plant leaves at near-infrared wavelengths. Barnard's star, a red dwarf located just 6 light-years from Earth, presents an intriguing case when considering the concept of a habitable zone. This region around a star is where conditions might be right for liquid water to exist on a planet's surface, a key factor in the search for potentially habitable worlds. For Barnard's star, the habitable zone is much closer to the star than it would be in our solar system. This is because red dwarfs are smaller and cooler than our Sun, emitting less energy. As a result, planets need to orbit closer to receive enough warmth for liquid water to potentially exist on their surfaces. However, this proximity comes with challenges. Planets orbiting so close to their star face intense stellar activity, including powerful flares and radiation that could strip away atmospheres and make the surface inhospitable. Additionally, these planets might become tidally locked, with one side always facing the star, creating extreme temperature differences between the day and night sides. Recent observations have suggested the presence of a super-Earth orbiting Barnard's star, but this planet lies beyond the estimated habitable zone, likely making it too cold for liquid water. The search continues for potentially habitable worlds around this nearby stellar neighbor, highlighting the complexities of applying the habitable zone concept to different star systems. Life on a planet orbiting Barnard's star, a red dwarf, would face several unique challenges. The most significant hurdle would be the intense radiation environment. Red dwarfs are known for their frequent and powerful flares, which can bombard nearby planets with high-energy particles and ultraviolet radiation. This constant barrage could damage or destroy any life forms not adequately shielded. Another major challenge would be the extreme temperature variations. Planets orbiting red dwarfs need to be much closer to their star to receive enough warmth for liquid water to exist. This proximity often leads to tidal locking, where one side of the planet always faces the star. The result is a scorching hot day side and a perpetually frozen night side, with only a narrow, habitable zone along the terminator, the boundary between day and night. The limited light available for photosynthesis poses yet another obstacle. Red dwarfs emit most of their energy in the infrared spectrum, providing less visible light for plant-like organisms to use for energy production. Any life forms would need to evolve alternative methods of energy generation or adapt to use infrared light efficiently. Lastly, the longevity of red dwarfs presents an intriguing challenge. These stars can live for trillions of years, far outlasting our Sun. While this provides ample time for life to evolve, it also means that any life forms would need to be incredibly resilient, capable of adapting to the gradual changes in their star's output over extraordinarily long timescales. Barnard's star, one of our closest stellar neighbors, offers a unique opportunity to expand our knowledge about the potential for life beyond Earth. Located just 6 light-years away, this ancient red dwarf has been a subject of fascination for astronomers for over a century. Its proximity allows for detailed observations, making it an ideal target for studying the conditions that might support life on other worlds. One of the most intriguing aspects of Barnard's star is its age. Estimated to be around 10 billion years old, it has existed for much longer than our Sun. This longevity raises questions about the evolution of planetary systems and the potential for life to develop over extended periods. By studying Barnard's star, scientists can gain insights into how planets and their atmospheres might change over billions of years, potentially creating conditions conducive to life. Recent discoveries have revealed the presence of at least one exoplanet orbiting Barnard's star. This planet, known as Barnard's star B, is believed to be a super-Earth, several times more massive than our home planet. While it orbits in the star's snowline and is likely too cold for liquid water on its surface, its existence suggests the possibility of other, potentially habitable planets in the system. The search for these worlds could provide valuable data on the frequency and characteristics of potentially life-supporting planets around red dwarf stars, which are the most common type of star in our galaxy. Furthermore, studying Barnard's star and its planetary system can help refine our understanding of the habitable zone concept. Red dwarfs like Barnard's star are much cooler than our Sun, which means their habitable zones are located much closer to the star. This proximity raises questions about how stellar activity, such as flares and radiation, might affect the potential for life on nearby planets. By examining these factors in detail, scientists can better understand the conditions necessary for life to thrive in diverse stellar environments, broadening our perspective on where we might find life in the universe. Studying Barnard's star presents several technological challenges for astronomers. The star's proximity to Earth, at just 6 light-years away, makes it an enticing target, but its small size and dim nature complicate observations. One major hurdle is the star's faintness. Barnard's star is a red dwarf, much smaller and cooler than our Sun, emitting only a fraction of the light. This low luminosity makes it difficult to gather enough light for detailed spectroscopic analysis, which is crucial for studying the star's composition and potential planetary system. Another significant challenge is the precise measurements required to detect any orbiting planets. The most effective method for finding exoplanets around nearby stars is the radial velocity technique, which detects tiny wobbles in the star's motion caused by orbiting planets. However, these wobbles are extremely small, requiring ultra-sensitive instruments and long-term observations to distinguish them from other stellar variations. The star's high proper motion, the fastest of any known star, also complicates long-term studies. As Barnard's star moves rapidly across our sky, astronomers must constantly adjust their instruments to track it accurately, adding another layer of complexity to already challenging observations. Adaptive optics technology has revolutionized our ability to observe Barnard's star with unprecedented clarity and detail. This advanced system compensates for the distortions caused by Earth's turbulent atmosphere, allowing ground-based telescopes to capture images nearly as sharp as those taken from space. For Barnard's star, this technological leap has been particularly significant. As one of our closest stellar neighbors, located just 6 light-years away, Barnard's star has long been a subject of intense astronomical interest. However, its dim nature as a red dwarf made precise observations challenging. Adaptive optics has changed that. enabling astronomers to study this ancient star with remarkable precision. With adaptive optics, we can now detect subtle changes in Barnard's star's position and brightness. This enhanced precision has allowed scientists to refine measurements of its proper motion, which is the fastest of any known star. It has also improved our ability to search for potential exoplanets orbiting the star, leading to the detection of a candidate super-Earth in 2018. Moreover, adaptive optics has revealed new details about Barnard's star's physical characteristics. We can now better estimate its size, temperature, and composition, providing valuable insights into the nature of low-mass stars and their evolution over billions of years. This improved observational power continues to deepen our understanding of our galactic neighborhood and the diverse stars that inhabit it. Space-based telescopes have revolutionized our study of Barnard's star, offering unparalleled clarity and precision in observing this nearby celestial neighbor. These advanced instruments, orbiting high above Earth's atmosphere, provide a crystal-clear view unobstructed by atmospheric distortions that plague ground-based observations. The Hubble Space Telescope has been instrumental in refining our understanding of Barnard's star's properties. Its precise measurements have helped astronomers determine the star's distance, motion, and physical characteristics with unprecedented accuracy. This information is crucial for understanding the nature of red dwarf stars, which are the most common type of star in our galaxy. More recently, the Transiting Exoplanet Survey Satellite, or TESS, has turned its gaze toward Barnard's star in search of potential exoplanets. While no confirmed planets have been found orbiting this star, TESS's sensitive instruments continue to monitor it for tiny dips in brightness that could indicate the presence of orbiting worlds. Space-based telescopes also play a vital role in studying Barnard's star's proper motion, which is the fastest of any known star relative to Earth. These precise measurements help astronomers better understand stellar kinematics and the dynamics of our local stellar neighborhood. As we continue to launch more advanced space telescopes, our knowledge of Barnard's star and similar nearby stars will undoubtedly expand, shedding light on the diverse stellar population in our cosmic backyard. Barnard's star presents a unique challenge for astronomers due to its extremely low luminosity. Despite being one of our closest stellar neighbors at just under 6 light-years away, this red dwarf star is too faint to be seen with the naked eye. To overcome this obstacle, astronomers employ a variety of advanced techniques and technologies. One key method is the use of large, powerful telescopes that can gather more light, allowing for clearer observations of dim objects like Barnard's star. These telescopes, both ground-based and space-based, are equipped with highly sensitive detectors capable of capturing even the faintest signals from distant stars. Additionally, astronomers often use long exposure times when observing Barnard's star. By allowing light to accumulate on their detectors over extended periods, they can build up a stronger signal and reveal details that would otherwise be too faint to detect. This technique is particularly useful for studying the star's spectrum and searching for signs of orbiting planets. Another approach involves using infrared astronomy. Since Barnard's star emits most of its energy in the infrared part of the spectrum, observing it at these wavelengths can provide valuable data that might be missed in visible light observations. This method has proven especially useful in studying the star's temperature, composition, and potential planetary system. Spectroscopy has played a crucial role in our understanding of Barnard's star, one of our closest stellar neighbors. Over the years, advancements in this field have greatly enhanced our ability to study this fascinating red dwarf. High-resolution spectrographs have been instrumental in detecting the subtle shifts in Barnard's star's spectral lines, allowing astronomers to measure its radial velocity with unprecedented precision. This has been key in the search for exoplanets around the star, as these minute velocity changes can indicate the gravitational influence of orbiting bodies. Improved infrared spectroscopy techniques have also been valuable in studying Barnard's star. As a cool red dwarf, much of its light is emitted in the infrared part of the spectrum. Advanced infrared spectrometers have enabled scientists to better analyze the star's composition, temperature, and other physical properties. Furthermore, the development of adaptive optics and space-based observatories has significantly reduced atmospheric interference, resulting in clearer and more detailed spectra. This has allowed for more accurate measurements of the star's properties and has helped in the ongoing search for potential planetary companions. Radio telescopes have played a crucial role in expanding our knowledge of Barnard's star, one of our closest stellar neighbors. These powerful instruments detect radio waves emitted by celestial objects, allowing astronomers to study phenomena that are invisible to optical telescopes. For Barnard's star, radio telescopes have been instrumental in measuring its proper motion across the sky. This red dwarf star has the fastest apparent motion of any star as seen from Earth, moving at a rate of 10 arc-seconds per year. Radio observations have helped refine these measurements, providing precise data on the star's movement and position. Furthermore, radio telescopes have been used to search for potential planets orbiting Barnard's star. By detecting minute variations in the star's motion, astronomers can infer the presence of orbiting bodies. Although no confirmed planets have been found, these observations have set important constraints on the types of planetary systems that could exist around this ancient star. Radio telescopes have also contributed to our understanding of Barnard's star's magnetic activity. As a red dwarf, it is prone to powerful flares and magnetic events. By monitoring radio emissions from the star, scientists can study these phenomena and gain insights into the star's internal dynamics and how they might affect potential habitable zones around it. Barnard's star presents unique challenges for astronomers due to its rapid movement across the night sky. This celestial object, located just 6 light-years from Earth, is racing through space at a remarkable speed of 140 kilometers per second relative to our Sun. Its high proper motion means it appears to shift position against the background stars faster than almost any other known star. This swift movement complicates long-term studies in several ways. First, it requires astronomers to constantly update their observational data and recalculate the star's position. What might be an accurate location one year could be noticeably off the next, demanding frequent adjustments to telescopes and other instruments. Moreover, the star's rapid motion affects our ability to detect potential planets orbiting it. The traditional method of finding exoplanets by observing a star's slight wobble becomes more challenging when the star itself is moving so quickly. Astronomers must carefully distinguish between the star's overall motion and any subtle variations that might indicate the presence of orbiting bodies. The high proper motion of Barnard's star also impacts our understanding of its interactions with interstellar matter. As it speeds through space, it encounters different regions of the interstellar medium, potentially affecting its observable characteristics over time. This makes it crucial for researchers to consider the star's changing environment when interpreting long-term observations, adding another layer of complexity to their studies. Computer modeling has revolutionized our understanding of Barnard's star and its behavior. This red dwarf, located just 6 light-years from Earth, has been a subject of intense study for decades. Advanced simulations now allow astronomers to predict its movements and potential planetary system with unprecedented accuracy. These models integrate vast amounts of observational data, including precise measurements of the star's position, velocity, and brightness variations. By processing this information, computers can create detailed simulations of Barnard's star's past and future trajectories. This has greatly improved our ability to track its proper motion across the sky, which is the fastest of any known star. Furthermore, computer models have been crucial in the search for exoplanets around Barnard's star. They help scientists analyze subtle wobbles in the star's motion, potentially indicating the gravitational influence of orbiting planets. In fact, these models were instrumental in the tentative detection of a super-Earth-sized planet announced in 2018. Perhaps most importantly, computer simulations allow astronomers to test hypotheses about Barnard's star's internal structure and evolution. By modeling its core processes and magnetic activity, scientists can better understand how this ancient, low-mass star has behaved over billions of years and how it might change in the future. Astronomers are constantly pushing the boundaries of technology to enhance our understanding of stars like Barnard's star. Advanced adaptive optics systems are being refined to counteract the blurring effects of Earth's atmosphere, allowing ground-based telescopes to capture sharper images of distant stars. These systems use deformable mirrors that adjust thousands of times per second to compensate for atmospheric distortions. Space-based observatories are also evolving. The James Webb Space Telescope, with its unprecedented infrared capabilities, is opening new windows into the study of cool, low-mass stars like Barnard's star. Its sensitive instruments can detect the faint heat signatures of these stars and potentially reveal previously unseen companions or planetary systems. Interferometry techniques are advancing, allowing multiple telescopes to work together as if they were a single, giant instrument. This dramatically improves resolution and sensitivity, enabling astronomers to measure stellar properties with unprecedented precision. For Barnard's star, this could mean more accurate measurements of its size, temperature, and even subtle surface features. Spectroscopic instruments are becoming increasingly sophisticated, capable of detecting minute shifts in starlight that reveal a wealth of information. These advancements are crucial for studying the composition, motion, and potential planetary companions of nearby stars like Barnard's star, helping us build a more complete picture of our stellar neighborhood. Interferometry techniques have revolutionized our ability to study distant stars with unprecedented precision, and Barnard's star is no exception. As one of our closest stellar neighbors, located just 6 light-years away, Barnard's star has been a prime target for astronomical observations. By combining light from multiple telescopes, interferometry allows astronomers to achieve resolution far beyond what a single telescope can offer. This technique has been crucial in studying Barnard's star, enabling researchers to measure its size and surface features with remarkable accuracy. The star's angular diameter has been determined to be less than 0.002 arcseconds, a measurement that would be impossible without interferometric methods. Interferometry has also played a key role in the search for exoplanets around Barnard's star. By detecting minute wobbles in the star's position, astronomers can infer the presence of orbiting planets. This technique led to the discovery of a super-Earth candidate orbiting Barnard's star in 2018, although further confirmation is still needed. Moreover, interferometric observations have helped refine our understanding of Barnard's star's physical properties, including its temperature, mass, and composition. These precise measurements contribute to our broader knowledge of red dwarf stars, which are the most common type of star in our galaxy. Barnard's star, a red dwarf located just 6 light-years from Earth, follows a dramatically different evolutionary path compared to our Sun. While our Sun is a middle-aged yellow dwarf star, Barnard's star is much older and smaller, with unique characteristics that set it apart in the cosmic neighborhood. The most striking difference lies in their lifespans. Our Sun is expected to exist for about 10 billion years before expanding into a red giant and eventually becoming a white dwarf. Barnard's star, on the other hand, is projected to shine for an astonishing 1 trillion years. This extended lifetime is due to its lower mass and cooler temperature, which allow it to burn through its hydrogen fuel at a much slower rate. Unlike our Sun, Barnard's star will never pass through a red giant phase. Instead, it will gradually increase in temperature and luminosity over billions of years, eventually becoming a blue dwarf before fading away as a white dwarf. This slow, steady evolution contrasts sharply with the more dramatic changes our Sun will undergo in its final stages. Another key difference is in their energy output. While our Sun emits a broad spectrum of visible light, Barnard's star primarily radiates in the infrared. This lower energy output means that any planets orbiting Barnard's star would need to be much closer to receive the same amount of warmth as Earth does from our Sun, potentially creating very different conditions for the development of life. Barnard's star, one of our closest stellar neighbors, is currently in the main sequence stage of its evolution. This red dwarf star, located just 6 light-years from our solar system, has been steadily fusing hydrogen into helium in its core for billions of years. As a low-mass star, Barnard's star burns through its fuel at a much slower rate than larger stars like our Sun. This efficient use of resources means that Barnard's star has been in the main sequence for an incredibly long time and will continue to remain there for trillions of years to come. Despite its proximity and importance to astronomers, Barnard's star is not visible to the naked eye due to its small size and low luminosity. However, its longevity makes it an excellent subject for studying stellar evolution in red dwarf stars, which are the most common type of star in our galaxy. The main sequence stage is characterized by stable hydrogen fusion, and for Barnard's star, this stability is expected to last far longer than the current age of the universe. This makes it a prime candidate for potential long-term studies of stellar behavior and planetary systems around low-mass stars. Barnard's star, one of our closest stellar neighbors, is a small, cool red dwarf that has been a subject of fascination for astronomers for decades. This ancient star is estimated to be around 10 billion years old, making it more than twice the age of our Sun. Despite its advanced age, Barnard's star is expected to remain in its current evolutionary state for an extraordinarily long time. Red dwarfs like Barnard's star have incredibly slow rates of hydrogen fusion in their cores. This slow burn allows them to maintain their current state for much longer periods than larger, hotter stars. In fact, astronomers predict that Barnard's star will continue in its present form for another trillion years or more. This remarkably long lifespan is due to the star's low mass and temperature. Barnard's star is only about 15% the mass of our Sun and has a surface temperature of around 3,000 degrees Celsius, less than half that of the Sun. These characteristics mean it consumes its nuclear fuel at an extremely slow pace, allowing it to shine steadily for an immense span of time. The longevity of Barnard's star offers a glimpse into the far future of the universe. Long after our Sun has exhausted its fuel and become a white dwarf, Barnard's star will still be shining, a testament to the enduring nature of these small, efficient stars. This extended timeline provides ample opportunity for astronomers to study the long-term evolution of red dwarfs and their potential for hosting long-lived planetary systems. Barnard's star offers astronomers a unique window into the life cycles of red dwarf stars. As one of our closest stellar neighbors, located just 6 light-years away, this ancient star provides valuable insights into the long-term evolution of the most common type of star in our galaxy. Red dwarfs like Barnard's star are remarkably long-lived, with lifespans that can exceed hundreds of billions of years. This particular star is estimated to be around 10 billion years old, more than twice the age of our Sun. Despite its advanced age, Barnard's star continues to shine steadily, demonstrating the incredible longevity of these small, cool stars. Observations of Barnard's star reveal that it is moving rapidly across the sky, covering a distance equal to the Moon's diameter every 180 years. This swift motion, known as proper motion, is a result of the star's close proximity to Earth and its high velocity through space. By studying this movement, scientists can better understand how red dwarfs interact with their galactic environment over extended periods. Barnard's star also teaches us about the magnetic activity of aging red dwarfs. Despite its advanced age, the star still exhibits occasional flares, suggesting that even elderly red dwarfs can maintain some level of magnetic activity. This information helps astronomers refine models of stellar evolution and magnetic field generation in low-mass stars, contributing to our broader understanding of stellar physics and the potential habitability of planets orbiting red dwarfs. Barnard's star, a small red dwarf located just 6 light-years from our solar system, serves as an excellent example of how stellar mass shapes a star's life cycle. With a mass of only about 16% that of our Sun, Barnard's star follows a distinctly different evolutionary path compared to larger stars. The low mass of Barnard's star significantly extends its lifespan. While more massive stars burn through their fuel quickly, Barnard's star conserves its resources, fusing hydrogen into helium at a much slower rate. This conservative approach to nuclear fusion means that Barnard's star will continue to shine for trillions of years, far outlasting our own Sun. Despite its longevity, Barnard's star will never reach the temperatures required to fuse helium into heavier elements. This limitation is a direct consequence of its low mass, which cannot generate sufficient gravitational pressure in the stellar core. As a result, Barnard's star will never expand into a red giant or experience the more dramatic late stages of stellar evolution seen in more massive stars. Eventually, after its incredibly long life, Barnard's star will slowly cool and fade, becoming a white dwarf. This final stage will occur without the spectacular events associated with the death of larger stars, such as planetary nebula formation or supernova explosions. The mass of Barnard's star thus dictates a quieter, longer, and less eventful stellar life compared to its more massive counterparts in the cosmos. Barnard's star, one of our closest stellar neighbors, is destined for a quiet and prolonged demise. As a red dwarf, it burns its fuel slowly and steadily, giving it an incredibly long lifespan. Scientists estimate that Barnard's star is already about 10 billion years old, making it more than twice the age of our Sun. Despite its advanced age, Barnard's star still has a long future ahead. Red dwarfs like Barnard's star can continue fusing hydrogen in their cores for trillions of years. This means that long after our Sun has expanded into a red giant and faded away as a white dwarf, Barnard's star will still be shining, albeit dimly, in the night sky. Eventually, after exhausting its hydrogen fuel, Barnard's star will enter its final phase of life. Unlike larger stars, it lacks the mass to fuse heavier elements or expand into a red giant. Instead, it will gradually cool and dim, transforming into a white dwarf. This process will occur so slowly that it would be imperceptible on human timescales. In its final state as a white dwarf, Barnard's star will be a small, dense, and cooling ember in space. It will continue to radiate its remaining heat for billions upon billions of years, slowly fading until it becomes a black dwarf, a theoretical object so cool that it no longer emits any light or heat. This ultimate fate, however, lies so far in the cosmic future that the universe itself may have changed dramatically by the time Barnard's star reaches this final stage. Barnard's star offers astronomers a unique window into the life cycle of stars. As one of our closest stellar neighbors, located just 6 light-years away, this small red dwarf provides an excellent opportunity to study the aging process of low-mass stars in great detail. Unlike our Sun, Barnard's star is much older, estimated to be around 10 billion years old. This advanced age allows scientists to observe the long-term evolution of red dwarf stars, which make up the majority of stars in our galaxy. By studying Barnard's star, astronomers can better understand how these common stars change over billions of years. One key aspect of Barnard's star that contributes to our knowledge of stellar aging is its extremely low level of magnetic activity. This reduced activity is a sign of its advanced age, as stars tend to become less magnetically active as they grow older. Observing this phenomenon in Barnard's star helps confirm theories about how stellar magnetic fields evolve over time. Furthermore, the slow rotation rate of Barnard's star provides valuable insights into the relationship between a star's spin and its age. As stars age, they typically slow down their rotation due to magnetic braking. By precisely measuring the rotation of Barnard's star, Scientists can refine models of stellar spin-down, which in turn helps in estimating the ages of other stars throughout the universe. Metallicity plays a crucial role in the evolution of stars like Barnard's star, shaping their characteristics and life cycles. In astronomical terms, metallicity refers to the abundance of elements heavier than helium in a star's composition. Barnard's star, a small red dwarf located just 6 light-years from Earth, has low metallicity compared to our Sun. For stars like Barnard's star, low metallicity means they formed earlier in the universe's history when fewer heavy elements were available. This composition affects various aspects of stellar evolution, including the star's internal structure, energy production, and lifespan. Stars with lower metallicity tend to be more compact and hotter than their metal-rich counterparts of the same mass. The reduced metal content in stars like Barnard's star also influences their ability to form planets. Fewer heavy elements mean less material available for planet formation, potentially resulting in fewer or smaller rocky planets orbiting these stars. However, this doesn't rule out the possibility of planets entirely, as recent discoveries have shown that even low metallicity stars can host planetary systems. Importantly, the low metallicity of Barnard's star contributes to its longevity. With fewer heavy elements, these stars burn their fuel more slowly and efficiently, allowing them to shine for much longer periods than metal-rich stars. This extended lifespan means that stars like Barnard's star will continue to illuminate the cosmos long after more massive, metal-rich stars have exhausted their fuel and died. Barnard's star, a small red dwarf, exhibits unique convection processes that set it apart from larger stars. Unlike more massive stars, Barnard's star is fully convective throughout its entire interior. This means that the star's energy is transported from its core to its surface primarily through the physical movement of hot plasma. In contrast, larger stars like our Sun have a radiative zone between their core and outer convective layer. This radiative zone transports energy through the absorption and re-emission of photons. The absence of this radiative zone in Barnard's star leads to more efficient energy transfer and mixing of elements throughout the star. The full convection in Barnard's star also impacts its magnetic field. The constant churning of plasma generates a strong, complex magnetic field that can cause intense stellar activity, including frequent flares. This is different from larger stars, where magnetic fields are often generated at the boundary between the radiative and convective zones. These convection processes contribute to Barnard's star's longevity. The thorough mixing of elements ensures that hydrogen fuel is continuously supplied to the core, allowing the star to burn steadily for much longer than larger stars. This efficiency in energy transport and fuel consumption is a key reason why red dwarfs like Barnard's star are expected to shine for trillions of years, far outlasting their more massive counterparts. Barnard's star offers us a unique window into the early universe and star formation processes. As one of our nearest stellar neighbors, located just 6 light-years away, this ancient red dwarf has been a subject of intense study for astronomers. Formed over 10 billion years ago, Barnard's star is significantly older than our Sun and belongs to a population of stars that emerged when the universe was still in its infancy. Its composition reflects the elemental makeup of that early era, with a notably low metallicity compared to younger stars. This characteristic indicates that Barnard's star formed from the primordial gas clouds that existed before multiple generations of stars had enriched the cosmos with heavier elements. The star's longevity and stability provide valuable insights into the life cycles of low-mass stars, which dominate the stellar population in our galaxy. Unlike more massive stars that burn through their fuel quickly, red dwarfs like Barnard's star operate at a much slower pace, allowing them to shine for tens of billions of years. This extended lifespan makes them excellent cosmic record keepers, preserving information about the conditions present during their formation. Studying Barnard's star also helps astronomers refine models of star formation and evolution in low metallicity environments. By comparing its properties to those of younger stars, scientists can trace how star formation processes have changed over the universe's history. This knowledge is crucial for understanding not only the early universe, but also the potential for life around the most common type of star in our galaxy. Barnard's star, a red dwarf located just 6 light-years from Earth, is significantly smaller than our Sun. This celestial neighbor, despite its proximity, is not visible to the naked eye due to its diminutive size and low luminosity. In terms of mass, Barnard's star is only about 1/6 that of our Sun, making it a true cosmic lightweight. Its diameter is equally unimpressive when compared to our solar system's central star. Barnard's star measures approximately 1/5 the diameter of the Sun, which means you could fit roughly 125 Barnard stars inside the volume of our Sun. This stark size difference highlights the diverse range of stellar objects in our galaxy. The compact nature of Barnard's star also affects its energy output. It emits only about 4/10,000ths of the Sun's luminosity, making it exceptionally faint despite its close proximity to Earth. This low luminosity is a characteristic feature of red dwarf stars, which are the most common type of star in our Milky Way galaxy. Barnard's star and our Sun exhibit notable differences in their composition, reflecting their distinct ages and evolutionary stages. Barnard's star is significantly older than our Sun, estimated to be around 10 billion years old compared to our Sun's 4.5 billion years. This age difference has led to divergent chemical compositions. Our Sun is primarily composed of hydrogen and helium, with trace amounts of heavier elements. In contrast, Barnard's star has a much higher proportion of metals, which in astronomical terms refers to elements heavier than helium. This increased metallicity is a result of its advanced age, as older stars have had more time to produce and accumulate heavier elements through nuclear fusion processes. The temperature of Barnard's star is also considerably cooler than our Sun. While the Sun's surface temperature is about 5,700 kelvins, Barnard's star has a surface temperature of only about 3,100 kelvins. This lower temperature gives Barnard's star its characteristic red color and classifies it as a red dwarf. Another key difference lies in their masses. Our Sun is a yellow dwarf star with a mass of about 1 solar mass. Barnard's star, however, is much less massive, with only about 16% of the Sun's mass. This smaller size and lower mass contribute to its longevity, as red dwarfs burn their fuel much more slowly and efficiently than larger stars like our Sun. Barnard's star and our Sun, while both stellar objects, have markedly different magnetic fields. Our Sun, a middle-aged yellow dwarf star, exhibits a complex and dynamic magnetic field that undergoes an 11-year cycle of activity. This solar magnetic field is generated by the movement of charged particles in the Sun's outer convective layer, creating a powerful dynamo effect. In contrast, Barnard's star is a much older and cooler red dwarf star. Its magnetic field is significantly weaker than that of our Sun, primarily due to its smaller size and lower mass. Red dwarfs, like Barnard's star, have fully convective interiors, which leads to a different type of magnetic field generation. This results in a more stable and less variable magnetic field compared to our Sun's cyclical changes. The weaker magnetic field of Barnard's star means it experiences fewer dramatic events such as solar flares or coronal mass ejections. However, it's important to note that even with a weaker field, red dwarfs can still exhibit strong magnetic activity relative to their size, often with longer-lasting star spots and more frequent flares than seen on our Sun. These differences in magnetic fields have significant implications for potential planetary systems around each star. The more stable environment around Barnard's star might be more conducive to the long-term survival of close-orbiting planets, while the dynamic magnetic field of our Sun plays a crucial role in shaping the space weather and habitability conditions in our own solar system. Barnard's star offers astronomers a unique opportunity to study stellar evolution and the life cycles of stars similar to our Sun. As one of our nearest stellar neighbors, located just 6 light-years away, Barnard's star provides a close-up view of a low-mass red dwarf star. This proximity allows scientists to observe and measure its properties with exceptional detail and accuracy. By comparing Barnard's star to our Sun, researchers can gain insights into the diverse range of stellar types and their characteristics. Barnard's star is much older than our Sun, estimated to be around 10 billion years old, which is more than twice the age of our solar system. This advanced age makes it an excellent subject for studying the long-term evolution of stars and predicting how our own Sun might change over billions of years. One of the most intriguing aspects of Barnard's star is its extremely low luminosity and cool surface temperature compared to our Sun. This difference highlights the vast spectrum of stellar properties and helps astronomers refine their models of stellar structure and energy production. Additionally, the star's slow rotation rate and low level of magnetic activity provide valuable data on how these properties change as stars age, offering clues about the future behavior of our own Sun. Studying Barnard's star also contributes to our understanding of planetary formation and habitability. Recent observations have suggested the presence of a super-Earth orbiting this red dwarf, expanding our knowledge of planetary systems around different types of stars. By examining the conditions around Barnard's star, scientists can better comprehend the factors that influence the formation and sustainability of life-supporting environments, both in our solar system and beyond. Barnard's star and our Sun are both stars, but they differ significantly in their characteristics and lifespans. Barnard's star is a red dwarf, much smaller and cooler than our Sun. This difference in size and temperature greatly affects their expected lifespans. Our Sun, a yellow dwarf star, has an estimated lifespan of about 10 billion years. It's currently about halfway through its life cycle, having existed for roughly 4.5 billion years. In contrast, Barnard's star, being a red dwarf, is expected to live much longer. Red dwarfs like Barnard's star burn their fuel much more slowly and efficiently than larger stars. This slow burn rate means they can continue to shine for an incredibly long time. Scientists estimate that Barnard's star could live for up to 1 trillion years, which is about 100 times longer than our Sun's total lifespan. This vast difference in longevity is due to the way these stars function. Our Sun fuses hydrogen into helium in its core at a relatively rapid rate, while Barnard's star does so much more slowly, conserving its fuel over an extended period. This comparison highlights the diverse nature of stars and their varying lifespans in our universe. Barnard's star and our Sun are both stellar objects, but they differ significantly in their energy production. Our Sun is a yellow dwarf star, classified as a G-type main sequence star, while Barnard's star is a red dwarf, classified as an M-type main sequence star. This fundamental difference leads to contrasting energy generation processes. The Sun, being larger and more massive, primarily produces energy through the proton-proton chain reaction in its core. This process fuses hydrogen nuclei into helium, releasing a substantial amount of energy in the process. The high temperature and pressure in the Sun's core, around 15 million degrees Celsius, facilitate this fusion reaction efficiently. Barnard's star, on the other hand, is much smaller and cooler than our Sun. Its core temperature is lower, which means it cannot sustain the same level of nuclear fusion as the Sun. Instead, Barnard's star relies more heavily on a different fusion process called the carbon-nitrogen-oxygen cycle. This cycle is more temperature-sensitive than the proton-proton chain and becomes dominant in stars more massive than the Sun. However, in Barnard's star, it operates at a much slower rate due to the lower core temperature. The energy output of Barnard's star is significantly less than that of our Sun. While the Sun emits energy at a rate of about 380 septillion watts, Barnard's star produces only about 400 billion watts. This vast difference in energy production is reflected in their surface temperatures and overall luminosity, with Barnard's star appearing much dimmer and redder compared to our bright yellow Sun. Barnard's star and our Sun exhibit notably different flare activities, reflecting their distinct characteristics as stellar objects. Barnard's star, a red dwarf star much smaller and cooler than our Sun, was long thought to be relatively inactive. However, recent observations have revealed that it does produce flares, albeit less frequently and with lower intensity than many other red dwarfs. Our Sun, a yellow dwarf star, displays a more consistent pattern of flare activity. Solar flares occur regularly, with larger events happening every few years during the peak of the solar cycle. These flares can release enormous amounts of energy, sometimes equivalent to billions of hydrogen bombs. The flares from Barnard's star, when they do occur, tend to be less energetic than those from our Sun. This is partly due to its smaller size and lower temperature. However, the impact of these flares on potential planets orbiting Barnard's star could be more significant, as planets would need to orbit closer to the star to maintain habitable temperatures. The study of flare activities in different types of stars helps astronomers understand stellar evolution and the potential for life around various star types. While our Sun's flares can affect Earth's technology and upper atmosphere, the more sporadic nature of Barnard's star's flares presents different challenges for potential life in its system. Barnard's star offers astronomers a unique window into the potential future of our Sun. As one of our closest stellar neighbors, located just 6 light-years away, this ancient red dwarf has been a subject of intense study for decades. Its advanced age, estimated to be around 10 billion years old, makes it significantly older than our Sun, which is about 4.5 billion years old. By examining Barnard's star, scientists can gain insights into the long-term evolution of low-mass stars like our Sun. This red dwarf has already progressed through much of its lifespan, providing clues about the changes our Sun might undergo in the distant future. One key observation is that Barnard's star is considerably cooler and less luminous than our Sun, reflecting the gradual cooling process that occurs as stars age. Furthermore, the study of Barnard's star has revealed important information about stellar magnetic activity and its decline over time. As stars age, their rotation typically slows, leading to a decrease in magnetic activity. This process has implications for the habitability of planets orbiting aging stars, as changing stellar conditions can significantly impact planetary atmospheres and surface conditions. Observations of Barnard's star also contribute to our understanding of how stars lose mass over time through stellar winds. This mass loss, though minimal for stars like our Sun, plays a crucial role in stellar evolution and can affect the orbits of any planets in the system. By studying these processes in Barnard's star, scientists can better predict how our own solar system might change as the Sun enters its later life stages billions of years from now. Barnard's star and our Sun have markedly different habitable zones due to their distinct characteristics. Barnard's star is a red dwarf, much smaller and cooler than our Sun. As a result, its habitable zone is significantly closer to the star itself. The habitable zone of Barnard's star is estimated to be roughly 20 times closer to the star than Earth is to our Sun. This proximity is necessary because Barnard's star emits far less heat and light than our Sun. A planet in this zone would need to orbit Barnard's star in a matter of days or weeks, rather than the year it takes Earth to orbit the Sun. Our Sun's habitable zone, by comparison, is much farther out and wider. It extends from about 95 million kilometers to about 160 million kilometers from the Sun. Earth sits comfortably within this range, receiving just the right amount of energy to maintain liquid water on its surface. The compact nature of Barnard's star's habitable zone presents unique challenges for potential life. Planets orbiting so close to their star may become tidally locked, with one side always facing the star. This could create extreme temperature differences between the day and night sides of the planet, potentially making it less hospitable for life as we know it. Barnard's star, a red dwarf located just 6 light-years from Earth, offers intriguing insights into the diversity of stellar environments in our cosmic neighborhood. Unlike our Sun, which is a yellow dwarf, Barnard's star is smaller, cooler, and significantly older. This comparison highlights the vast range of conditions that could potentially support life in the universe. The longevity of red dwarfs like Barnard's star, which can burn for trillions of years, provides ample time for life to potentially emerge and evolve on any planets orbiting them. This extended timescale contrasts sharply with the roughly 10 billion-year lifespan of our Sun, suggesting that if life exists around red dwarfs, it might have had much longer to develop and diversify. However, the lower energy output of Barnard's star means that its habitable zone, the region where liquid water could exist on a planet's surface, is much closer to the star than in our solar system. This proximity could expose planets to intense stellar flares and radiation, potentially challenging the development of life as we know it. Yet, this very challenge might drive the evolution of life forms adapted to these harsh conditions, expanding our understanding of life's potential. The study of Barnard's star and similar red dwarfs is reshaping our search for extraterrestrial life. It encourages scientists to consider a wider range of environments and adapt our detection methods to account for the unique characteristics of these ubiquitous stellar systems, ultimately broadening our perspective on where life might thrive in the cosmos. Currently, there are no major space missions specifically dedicated to studying Barnard's star. However, this nearby red dwarf remains a target of interest for astronomers and exoplanet hunters. Ground-based observatories and existing space telescopes continue to monitor Barnard's star as part of broader surveys and research programs. The European Space Agency's Gaia mission, while not focused solely on Barnard's star, is providing unprecedented precision in measuring the positions and motions of stars. This data helps refine our understanding of Barnard's star's properties and potential planetary system. Future missions like the James Webb Space Telescope, though not dedicated to Barnard's star, will have the capability to study its atmosphere and search for signs of exoplanets. Additionally, proposed missions such as the Large Ultraviolet Optical Infrared Surveyor might include Barnard's star in their observing programs, potentially revealing new insights about this intriguing stellar neighbor. As our technology advances, we can expect more detailed studies of Barnard's star, even if not through dedicated missions. Its proximity and the possibility of hosting potentially habitable planets make it an ongoing subject of scientific curiosity and exploration. Future advancements in telescope technology hold great promise for enhancing our observations of Barnard's star. As one of our closest stellar neighbors, Barnard's star has long captivated astronomers, and improved instruments could unveil new secrets about this ancient red dwarf. Next-generation space telescopes with larger mirrors and more sensitive detectors will allow us to capture clearer, more detailed images of Barnard's star. This increased resolution could help us better understand its surface features, including any star spots or flares that might be present. Such observations could provide valuable insights into the star's magnetic activity and how it has evolved over its long lifetime. Advancements in spectrographic technology will enable more precise measurements of Barnard's star's motion and composition. This could lead to improved detection of any planets orbiting the star, potentially confirming the existence of the candidate planet Barnard's star B or revealing other, previously undetected worlds in the system. Interferometry techniques, which combine light from multiple telescopes to achieve ultra-high resolution, may allow us to directly image the surface of Barnard's star. This would be a remarkable achievement, giving us our first detailed look at the face of a star other than our Sun, and potentially revolutionizing our understanding of red dwarf stars. Barnard's star continues to intrigue astronomers with several unresolved mysteries. One of the primary questions revolves around its planetary system. While a super-Earth exoplanet was confirmed orbiting the star in 2018, scientists are still searching for additional planets that may be lurking in its vicinity. The potential for habitable worlds around this nearby red dwarf remains a topic of intense interest and ongoing research. Another area of investigation focuses on the star's age and evolutionary history. As one of our closest stellar neighbors, Barnard's star provides a unique opportunity to study the life cycle of low-mass stars. Researchers are working to refine estimates of its age, which could shed light on the formation and evolution of the Milky Way's older stellar populations. The star's magnetic activity and flare behavior also present intriguing avenues for study. Understanding how these processes work in cooler, older stars, like Barnard's star, can help scientists better comprehend stellar physics and the potential impacts on orbiting planets. This knowledge is crucial for assessing the habitability of worlds around red dwarf stars, which are the most common type of star in our galaxy.